it looks, I was gonna say, somebody was recording. All right, Mark's pushing buttons over here and the computer's talking to me. All right, so it's full of organic matter, but it's not gonna function. Is water gonna move into that soil? Are roots gonna grow down through that soil? Is that organic matter gonna cycle properly because their microorganisms are thriving? Or when you look at the picture on the right, in this picture from Kewaunee County, are those plants much happier, right? We talk a lot about, as soil scientists, we talk a lot about granular structure. You should get really excited and giddy about the granular structure you see in that picture. Is everybody getting excited and giddy? Okay, virtual world, they're not excited or giddy here. So we're gonna have to liven these people up a little bit, all right? You should be excited. One of you, I think it was told me that you only got a couple hours sleep last night. Okay, you're only gonna get a couple hours sleep tonight because you're gonna be thinking about this granular structure and what you need to grow pumpkins, right? In our environment where we tend to get excessive rainfalls, you need that water to drain, right? That soil, that Kewaunee soil is going to drain properly. That granular structure is gonna allow for that air to move in there. It's not gonna be saturated, right? It's gonna allow for root growth. Oftentimes, and that's why when I took that picture, I wanted you to see all of those roots dangling down through that profile. If you notice, the cover crop on top is only a few inches tall, but that root system of that cover crop is deep down into that soil because it has beautiful structure. That plant is able to get down, get the nutrients, get the water it needs, right? It's better, healthier plant because it's able to get its roots into that soil system versus the one on the left. So when we talk about soil health, again, this is what I look at when I talk about soil health. How do I get my soil to go from the one on the left to the one on the right? And it's going to take time, right? It's going to take a lot of time, but it can be done because ultimately we want that soil to function as a vital living organism. So how do we adopt these practices? We're going to have to support soil biology. And so we could dive deep into the philosophies of how aggregates form, right? It involves roots and organisms. We could dive into how nutrient cycles. It involves soil organic matter and organisms. We could talk about water dynamics, right? It has to do with organic matter, which is decomposed by those organisms. Organisms are right there in the central part of making and allowing and getting that positive function out of our soil. So we're going to talk particularly about 3 practices in this first part. Managing soil fertility, right? Nutrients. Talking about minimizing disturbances. So some of you aren't going to like this one. Oftentimes, if I talk to just the general farming community, gardening community, and I tell them that we should stop tilling, it's all everybody tries to basically kill me at that point in time because we really like our rototillers, right? We love to have that clean, bare soil in gardens. I'm guessing some of you are the same. So I've been told that you like lay on the ground and love on these vines, gently tapping and putting soil around each, whatever they're called, and roots go into the ground and you weed and you do all sorts of amazing things, right? You're up close and personal with that soil. Oh, it'll make it easier because you're still looking at this slide. So this is where I can't multitask. Sorry. Thank you, Mark. Mark's got me. All right. And promoting aggregate formation and stabilization, because like I said, that is where I love to go. So how many of you know how many organisms are in a soil? No one does. Some poor soul tried to count and estimate them, right? So what are our best estimates? So we got some smarty pants in here. They're catching me already, all right? What is an estimate in a teaspoon of healthy soil? This is coming out of the USDA NRCS Soil Biology Primer. We estimate in a teaspoon of healthy soil about 1 billion bacteria. We're looking at several yards of fungi. And I live up near Shawano, so you'll see from a forest system and a beautiful, healthy forest system, they estimate in a teaspoon of soil, there could be up to 40 miles of fungal hyphae in a teaspoon of soil, right? So most of us can't even imagine what kind of life there is out in the soil, and we can't even imagine what that does. We're talking about 2 species, right? We just talked about bacteria and fungi. In all reality, there's also important larger critters, such as the protozoa and nematodes. And again, most people freak out when I say nematodes because we automatically go to the bad ones, the root knot, nematodes, everybody that's causing damage. But realize, I think right now on that estimate, there's 7,000 to 10,000 different species of nematodes, and most of them are beneficial. They're out there feeding on that bacteria, helping to keep that soil food web organized. And so that one organism isn't dominating or another. It's all about balance. It's about keeping that ecosystem in check. There's also arthropods. There's earthworms, right? So I was talking to the guy from Kakana, right? How do we help to start to build soil structure in a heavy clay soil? For those of us in gardening, earthworms, and agriculture production, earthworms are where it's at, right? Why? Anyone under the age of 18? Why are earthworms? Where is it at? So teenagers do not care about earthworms. All right, so earthworms, right? When we think about particularly water infiltration, when we think about aggregation, when we think about how that soil properly functions, earthworm guts are completely inefficient, right? So what goes in is almost the same as what comes out. So it starts to decompose that organic matter, but it makes that organic matter more readily available to the organisms that come after it, such as the fungi and bacteria. Those earthworms help to create those long pore channels, and particularly the anisic worms, the night crawlers that go up and down, that help to get water to drain through our soils. Those earthworms in their earthworm casts, how many of you use earthworm casts? You betcha. Why do you use them? Because it has that beautiful granular structure that's going to keep you up at night really excited? Or because, right? Or because they're full of ammonium, they're full of nutrition, right? We use them as a biotype fertilizer, right? So this is where when we talk about organisms, we are going to think about them as being the foundational source of how that soil functions over time. And I apologize, I want to wander around, but I'm tethered to this podium here. So there's 18 essential nutrients for plant growth. How many of you knew that? All right, there used to be 17. At one time there were 16. If you talk to some people, they still think there's 16, 17. We're still in arguments over how many essential nutrients there are, but there's somewhere between 16 and 18, depending upon who you talk to. All right, I divide them up into, do they come from the air or do they come from the soil? You notice when they come from the air, we're looking at carbon, hydrogen, and oxygen. We get these, plants get these through water as well as atmospheric air, right? From the soil, we're looking at, you'll notice I listed these out separately: nitrogen, phosphorus, potassium, calcium, magnesium, and sulfur. Those are our macronutrients. Those are the nutrients that are needed in larger amounts than the micronutrients, which are listed in the last column. I always have to point this out. They are not more important. They are simply needed in larger amounts. This is where oftentimes when I work with any kind of producer, when we think about, oh, my plant's not growing well, I'll add more nitrogen. My plant's not growing well, I'll put down some NPK. My plant's looking kind of yellow, I'm going to add some more fertilizer. Well, do you know what you're actually deficient in? Because there's 18 essential nutrients, more than just nitrogen, more than just NPK out there. And we need to understand that. We also need to understand that when you look at that list, how many of you have ever fertilized for nickel? So someone has. Most of you are like, nope. Right? Why? When we look at these, particularly the micronutrients, oftentimes we rely very heavily on nutrient cycling. We rely very heavily on mineral weathering. So the breakdown of the sand, silts, and clays to provide these nutrients, we rely very heavily on microorganisms to put these nutrients back into solution for us. So when we think about this, this is bringing us back to microbes, soil organic matter. This is what is going to help us produce. So is the sky's the limit for organic matter? Because I know you all read the peer-reviewed research on organic matter. You know, what's the best amount? Because who doesn't? That would be me. No, come on, liven up. So yields in typical agronomic crops, we say that yields will increase up to approximately what % organic matter, and then they level off. About 4.5. After that, yields will level off. So when I look at most producers, how many of you know your soil test organic matter levels? Those of you on the phone in the back, do you know your soil organic matter levels? No. You should know, Coleman, you don't have a whole lot of organic matter up there, man. I'm teasing. So this is where I also used to teach college at 8 o'clock in the morning. Have you ever tried to teach college students at 8 a.m. in soils on a Friday morning? And they weren't even Wisconsiners, they were the Missourians, and they were just as bad as what you'd expect a Wisconsinner would be like on 8 a.m. on a Friday morning. Most of us do not have organic matter levels if you're in this range, right? So if you do, congratulations. When I look at most farms, I'm warning in the 1 to 2% range. So there's always room for improvement, okay? So this is what we're talking about here. These 18 essential nutrients. There's some beneficials out there. So these haven't quite been studied enough, basically, in my terms, they haven't been studied enough to put them in the essential category just yet, right? Sodium, silicon, selenium, and vanadium. So vanadium's been studied for years. It's on the cusp of being brought into that essential nutrient realm. So what is the role of soil biology? This is the key, right? Healthy soils, soils that have life will cycle nutrients better. So usually when we think about it, I don't know what it is in pumpkins. As Jim said, I'm not a pumpkin expert, but I can tell you what it is in corn. So when I talk to a typical corn producer, what % of the nitrogen do I expect for that corn crop to come from the soil? 60 to 70% of the nitrogen required to grow a corn crop, I expect to come from the soil. I am only supplementing the other 30 to 40%. Right? When you think about that, that's tremendous, right? You are relying so heavily on that soil to provide nutrients, so heavily that we need to make sure that we're managed that for these aerobic, these facultative, we'll get that word out yet, organisms that are out there to help to break this down. And it's big and small, all right? So when you see those millipedes, I used to be a county extension agent, and every fall, somebody would call me because there's 10,000 millipedes sitting out in their driveway when it got cold, all those little brown creepy crawly bugs, and they wanted to kill them somehow. It's like, no, they're very important. Those creepy crawlies that you see out there are a very, very important part of that organic matter decomposition cycle. I'll get that out. Oh, it was a long drive from Shauna this morning, and I didn't have my caffeinated coffee. So 80 to 90% of all decomposition is done by the creepy crawlies, is done by the macroorganisms, is done by the things that you can see. The rest is done by microorganisms. So when we talk about nutrient cycling, when we talk about healthy soils, I'm talking big critters, mites, millipedes, centipedes, those little beetles that you don't like so much. They're a very important role, as well as the bacteria, fungi, and Acinetobacters and everybody else. So when we look at soil organic matter, what is it? It's plant residues, animal residues, and microbial residues, but in some stage of decay. So I know this is what's always fun, talking with these groups. I know you're up on this. How many of you have heard about active organic matter versus stable organic matter? All right, you're nodding. What's active organic matter? Oftentimes I call it the fresh dead, right? It's the fresh dead stuff. It is only undergone primary decomposition. It's new. It may have, that organic matter may have been in the soil maybe 5 to 10 years. Right? It's full of carbon. It is full of nutrients. It is full of the good stuff that those microorganisms need to sustain themselves. That stable organic matter, the stuff that we call humus, it may have been in your soils thousands of years. Right? It's stable. It's been broken down. It plays a very, very important role in your soil, nutrient retention, aggregate stability, but we need to have both. We need to have that long-term, and we need to have this fresh. And this is what's key. If you want to maintain nutrient cycling, you want to maintain these microbial communities, you are constantly needing to put in fresh organic matter. That is their food source. That is their energy source. That is their nutrient source. That's what's key to this process. So what is your soil organic matter level? We already asked that. So I worked with the NRCS just in general. And when I talk about, I work up in Northeast Wisconsin. Again, when I work with most farmers, I'm looking at soil organic matter somewhere between 1% and 2%. We went out and we sampled what was the native organic matter level, quote unquote, went into that mature forest that hadn't been clear cutted in a long period of time, hasn't been tilled since we know of, since European invasion. We're looking at mean organic matter levels in those natural soils, as you can see, somewhere between 6% in the sandy soils of Shawano, up to 10% up in the heavier soils of Kewaunee. These were our natural organic matter levels to the 6-inch depth. So where are we at now? And where can we go? Which nutrient is most important? The one that's the lowest. So Liebig's law of the minimum, is that correct? So if you look, Liebig's law of the minimum states that the nutrient that, or the factor, plant growth factor, it could be sunlight, it could be space, it could be water. The nutrient or growth factor that's found in the least amount is controlling yield. That's not necessarily true. We know that, so they went on, it's a great way to talk to you about it. And that's why most of us have learned about Liebig's law of the minimum. And it's probably true for our mobile nutrients, such as nitrogen. But in all reality, when we look at our immobile nutrients, those things such as phosphorus, potassium, many of the micronutrients, it's going to follow the Michalik-Ball equation, percent sufficiency. And why I point this out is to get us to thinking about, I don't want to use the word balance, but to think about all of these nutrients are needed in order to produce maximum yield. You'll see in this, I'm going to have to move this, just give me a second, I need to move my screen. When we look at Michalik-Ball equation, what it's saying is that for every nutrient that's deficient, you're losing a percent of yield. So if you look at that table, it's showing maximum yield when NP and K are sufficient. It's just looking at these three nutrients. This is corn yield, 150 bushel an acre. If we're shy of K, you notice we only achieve 80% of max. We get 120 bushels. If we're shy of P, we get 60% of max. But if we're shy of both P and K, what happens? It's a multiplicative, right? We are losing more than just the nutrients that we supply. There's a compounding effect of all nutrients that are deficient. This is an important concept when we think about fertilization, right? Particularly for you all. And this is why it's really fun to talk to you, because I don't have to worry about economics, right? I don't have to worry about making you profitable when growing giant pumpkins, because I'm guessing there is no such thing as profitable in giant pumpkins, right? Just taking a guess, all right? It's just got cost. I don't know, some of you recouped $100 today. I'm guessing that may offset maybe the water required to lay on the ground and weed all these things or bury the roots or whatever y'all are doing.
Some of us go to California to wear pumpkins too.
Some of you go to, so yeah, we're not at all worried about recouping the cost of fertilization. So for you all that, when we look at this, it could be beneficial for you to, how many of you do tissue tests? All right. How else are we gonna gauge micronutrient availability? We're not. So tissue test is our best guess. And I'm gonna use the word guess. It's the best science we have right now, but it's still the best guess of gauging what is out there and is it sufficient? Because even if that little bit of nickel that we don't supply, if it's in short supply, it's gonna reduce yields. For some of you, it's more important than others. So in your heavier clay soils, you may have all the nutrients you need. You just have to get to them because you have a soil compaction problem or a tight soil problem. For those of you who farm in sands, which I'm used to, my backyard is a loamy sand. Right? It is pretty much siliceous quartz minerals. There's no nutrient out there. And if I was to grow giant pumpkins in my backyard, I would have to basically spoon feed almost all 18 essential elements to make it grow. Because my soil, in the status that it's in right now, doesn't supply it. Some of you have a completely different aspect, but it is important, right? That all 18 are there. Liven up, all right? I didn't even get into the chemistry, for God's sakes. We didn't talk about the oxidation reduction potential of all these nutrients and what happens when they become saturated, right? What forms? We didn't talk cations, anions. I didn't talk about isomorphic substitution of the tetrahedral layer to siliceous clays in order to increase the CEC. We didn't go there, all right? It's a smile. We're doing a general overview, all right? Is there gonna be a test? Yes. So tell me about, so the first question will be, tell me about tetrahedral layers, octahedral layers, and the isomorphic substitution and spectitic clays in the Valley of Wisconsin. There you go. That's the problem with soil scientists is we have this entire language and I have to remember to speak English, all right, when I come to talk to people, because you don't give a hoot about smectitic clays where they are my life, all right? So when we talk about that role of soil pH, right? If I don't care who I'm talking to, pH is the #1 important factor in controlling fertility within your soil. One of you is agreeing with me. Thank you. All right, the rest of you are staring at me, right? Why? Because it has to do with all of this chemistry that's involved in which form of nutrient is going to be out there in the soil. Nutrients can only be taken up if they're dissolved in water. And this is a real issue for some of us because for some of you on high pH soils, Kewaunee County, right? You have high pH soils, I'm guessing? 7, that's high pH, right? I work with soils up to 8 and 8.6, right? What happens when I start to put nutrients on a soil that has a pH of 8.6, particularly when I put phosphorus on a soil that has a pH of 8.6? I can dump, not literally, but I can dump phosphorus onto that soil, and as soon as that phosphorus dissolves, it's going to react with available calcium, tie it up, and that phosphorus becomes unavailable. So even if I put fertilizer to that soil, because of the pH conditions that are in there, I can't maintain solubility of that nutrient in order to keep that plant growing. I have hellacious times trying to keep micronutrients available in these high pH soils. So when you look at this chart, right, this is basically when you look at these bars, when the bar is wide and green, that means that the nutrient is available. And as that bar tapers down and turns from orange to yellow to red, that means that that nutrient becomes less available. Here's where soil becomes a very delicate balancing act. You'll notice that, those macronutrients, the NPK, calcium, magnesium, and sulfur, tend to be more available at higher pHs. So pHs above 6.5. Micronutrients, except for molybdenum, which doesn't follow the trend, micronutrients tend to be more available when the soil is lower pH. So there is a very, very, very delicate band right there. If you in this graph, it's in that range from 6.5 to 7, where we can kind of optimize the availability, chemically at least, the availability of our macro and our micronutrients. So I was looking at the slides earlier when we were chatting about the optimal pH range for pumpkins. I think you said 6.3 to 6.5. I love it. Yes, sir. You can have all of this. Like, we can put this as a PDF and send it to you. So this is key. If your pH is too low, what do? It's cheap and easy. You lime it. Ooh, I love, add gypsum. Ooh, this is my favorite myth to dispel. Yes! Woo! I'm excited. Sorry, online people. Here we go. Woo! All right. Now, huh? No, I don't care about the sulfate. Gypsum's not going to do anything to your pH. Oh, this is what's cool. Oh, calcium sulfate does it. Calcium sulfate, gypsum doesn't change your pH.
Does it change the availability of calcium sulfate?
Yes, it's a fertilizer. It's not a liming material, right? So the reason I put that, there's a lot of myth out there that when we think about liming materials, everybody think in order to be a liming material, you just have to contain calcium. No, that's one part of it. The definition of a liming material is it must contain a base cation and it must contain a portion of that molecule that neutralizes acidity, right? So when we think about, I wish I had this diagram in here, right? So when you take calcium carbonate, the lime, a typical lime, right? What happens? That calcium carbonate dissolves, okay? So I have the calcium portion and I have the carbonate portion. The calcium portion goes out and it knocks hydrogen ions, it knocks acids off your cation exchange sites. It gets those hydrogen ions back into the soil water. Now what happens? This carbonate portion reacts with those hydrogen ions to produce water and carbon dioxide, water and a gas. That's how pH changes, is I take free hydrogen ions, I take free acids, and I lock them up in a water molecule. That's why pH changes. I get rid of hydrogen ions. I lock them in water. When I add gypsum to the soil, it doesn't do that. The sulfate portion doesn't react to form water. So gypsum is an excellent, I use it a lot as a sulfur fertilizer. I use tons and tons and tons of gypsum in my typical traditional agriculture for sulfur fertilizer. I don't use it to change pH.
How about gypsum for changing soil structure in place?
Ooh, gypsum for changing soil structure in clays. So this is where Jim's gonna make fun of me as a scientist, right? So I'm gonna tell you that the peer-reviewed literature tells you that it has minimal effect. Gypsum does not improve soil structure in most soils.
Will it add calcium?
It will add calcium. Ding, you got that one because it's calcium sulfate. All right? Well, it could if you added too much phosphorus, and this is where the chemistry gets fun. Right?
Go back to the soil structure. Can you
So yeah, I can definitely explain to you why gypsum in most soils. And I have a slide later on that'll tell you that everything works once and nothing works every time, right? So gypsum, when I worked out west, I used gypsum all the time to improve soil structure. It sounds really strange that it works there, but not here. But it would only work in particular soils out west. If my soils were high in sodium, right? Oftentimes sodium chloride, right? Or sodium carbonate. Sodium, here's where the chemistry gets fun. All right, sodium is a monovalent, meaning it has one positive charge, right? It's also huge. Its hydrated radius is huge. So what it does is if this was my clay, I'm sorry, online people. If this was a clay and I'm a huge sodium ion, right, I would get stuck to the CEC, right? But I'm huge. I wouldn't let another clay come near me, right? So I can't aggregate because I have all of this huge sodium ion pushing all of my clay particles apart. Calcium is not that way. We don't have a lot of sodium in our soils. Therefore, we have these divalent cations, right? So I'm a little calcium ion, right? So I'm gonna have a much smaller hydrated radius. Because of that, clays can come closer together and I can get aggregation. So gypsum works well to improve aggregation when sodium is dominating the system. We simply don't have that. We have plenty of calcium, we have plenty of magnesium, potassium out there. So gypsum oftentimes, I'm not telling you that it doesn't, but the research, large scale research says under most situations, gypsum does not improve soil structure.
So then why do you use gypsum?
I love it as a fertilizer source. I love it as sulfur. You're gonna find that most of our soils, particularly those of you on sandy soils, because the Clean Air Act of 1970, we removed sulfur from emissions in the United States. We cleaned up our scrubbers, right? We put on scrubbers. We took sulfur out of diesel fuel. Before 1970, I used to get a lot of free sulfur falling out of the sky as acid rain. When I cleaned up the atmosphere in the 1970s, I don't get as much sulfur. And now what we're seeing is those sulfur deficiencies starting to appear, partially because we're not getting that free sulfur out of the sky, partially because we've driven our organic matter levels down so low, much of that sulfur was cycling out of our organic matter. And in traditional agricultural systems where we depleted organic matter, I'm just not getting that natural sulfur to cycle through. Gypsum is a great amendment. Like I said, I use it as a fertilizer source. I don't use it as a liming material and I don't use it as a improved soil aggregation. You might, and I'm not saying that you don't see benefits from it, but I'm saying large scale research says that over generalization, it doesn't. Yes, sir. 21 or 24, isn't it? I don't remember. It's in the 20s. 23, yeah. And it depends upon source. This is where there's two kinds of gypsum. You can get natural gypsums and you can get basically flue glass. So byproduct out of an industry. So there's two different kinds of sulfur, man-made basically, as well as natural. Ooh, that's where sulfur comes into play. This is where, yes, this is where sulfur comes into play. And this is where that confusion comes in. How do I lower pH? Elemental sulfur, not a sulfate, elemental sulfur. The yellow stinky powder that comes from volcanoes, right? That lowers pH. We can also use iron, we can use organic matter over time, but the quickest way to lower pH, and it's still not very quick, in particularly some soils, is to use elemental sulfur. And it's a large amount of elemental sulfur. For your scale of agricultural production, it works. For large scale agricultural production, it doesn't. Yes, sir. Oh, no, sorry people online, we're never gonna advance slides. So the question was aluminum sulfate, all right? So for you all, oh, heck no, not aluminum sulfate. Why is Jamie freaking out over aluminum sulfate? Yes, yes, it will drive pH down. I can't move, this is the problem. I'm tethered to this computer, I can't wander around. It's like, oh no, not aluminum sulfate. We would use it on blueberries because they're more aluminum tolerant. How tolerant? Aluminum is toxic to organisms. It's toxic to roots. It's toxic. Read your deodorant, right? Does anybody do that? So I know you all do. You don't lie to me. All right, you get bored and you read the ingredients on your deodorant, right? What's in there? Aluminum. Aluminum is toxic. It's killing the bacteria that cause odors in your underarms. That's why we use it. Aluminum's toxic. It's particularly toxic to roots. So when I get, and that's why you'll notice in this diagram, you notice after 5.5, pH of 5.5, things just go really bad in this diagram, right? Why? At a pH of 5.5, aluminum becomes soluble. So here comes back to the chemistry again. Aluminum becomes soluble and we start to basically burn the root systems off of aluminum intolerant plants. So when I'm talking about, if for many crops, if you were growing, you know, you were a standard agricultural producer, we can maybe tolerate aluminum, but because it looks like every 1/10 of a pound makes a difference to you, right? I don't want to stunt that root system at all. So I would stay away. I would stay away from aluminum sulfate. If I had to choose one, I'd choose an ammonium sulfate, right? Ammonium, nitrogen-based fertilizers will drive pH down over time, but I definitely stay away from aluminums. Yes, sir.
So a common amendment, azomite.
Yep.
High in aluminum. What's your thoughts on that?
I would stay away. If so, you know, it's one of those, it's how much are you putting on?
I don't use it, but I know other growers do because it's a trace mineral type thing or whatever.
Yeah.
But I don't use why I've never had it.
I wouldn't, so because of the growing situation you're in, right? I wouldn't use it. I wouldn't use any product that had high amounts of aluminum. And so if it contains trace amounts of aluminum, no big deal. You'll notice trace amounts of aluminum, particularly if your pHs are higher, that aluminum will get tied up as a hydroxide or oxide and it goes away. But in your special growing type situation, I might want to try and avoid that. But the impact, the risk on a higher pH soil is probably minimal. But again, every 1/10, 100th of a pound seems to count. So I wish it did for me, right? If only that worked in humans, this would be awesome, right? So I wouldn't have spent all COVID seeing how, if I could lose weight, right? I've actually been seeing if I could gain a 1/10 of a pound. That would have been fantastic. All right. It would have made this isolation for the last year so much more fun. All right. Questions? These are awesome, right?
I want to go back to gypsum.
Gypsum, yeah.
Gypsum for a sulfur source, but continuing adding gypsum is going to raise your calcium and then your base saturation.
Now you're going to make me go into base cation saturation ratios and is there an ideal balance between a calcium and a magnesium and a calcium and potassium and this and that or whatever. Science says no. So
like
it's
all right with this old stuff or whatever.
Albrecht, yep.
Yeah, you guys don't deal with that. Are you looking
No.
at more ideal, just certain levels or certain available levels in the soil?
Yep, it's based upon the percent sufficiency. So this is where science, so the science, so Neil, I think it was Neil Albrecht out of the University of Missouri, so it was developed and it's hung on because I think intuitively makes sense that you'd want to balance things in your soil, right? And to a point, there's some validity to it. But when we've gone back now since the base cation saturation ratio was developed and it was implemented, large-scale university research across the United States has shown that is not the best way to manage nutrients in a soil. It's based upon this percent sufficiency type model. So the chemistry, if you haven't figured out, the chemistry is extremely complex. So, and we can talk later on. I can diagram this out for you mathematically, why it works in some soils. And it does. The balancing cations in some soils will work, particularly high CEC soils, just simply because you have so many cations out there. In lower CECs, it doesn't make a difference. So for example, just to drive that home, you're all looking at me strangely. So the soils I work with have about a CEC of 5, right? Nothing, basically, right? So if I have a sandy soil with a pH of, with a CEC of 5, does it really matter for plant growth that I've ideally balanced out the calcium and magnesium on my 5 CEC sites? Is that what's controlling my plant growth, or simply because it's not available? It's not even there. So this is where it works. It works in higher CEC soils, but it's scientifically been, universities will not support it. How do we put that way? And this is what's fun. Jim said, they're gonna eviscerate you. I'm like, yes. All right. They're gonna because there's philosophy, there's what's worked on your farm, and there's what science tells us, right? And this is what's cool about soil science is we can all be right in a particular situation, right? That's what's neat about soils is they're highly variable. Yeah.
Instead of a guy, okay, I had, 70% calcium, 50% magnesium, 6-7% potassium on a standard soil test, and there's other soil tests available that show actually what's available currently. Is that what we need to be looking at when we're
I will tell you that all the work that we've done in Wisconsin, I don't know that we've ever identified a calcium deficiency in any soil. Magnesium, if I'm running cattle, I may have some magnesium deficiencies, and now I have breast tetany in my animals, so because of a different uptake imbalance. But I oftentimes, if they're in the sufficiency levels, you're talking about these water-soluble, water-extractable nutrients, which is called the Haney test. The problem with the Haney test is it's not calibrated for Wisconsin. What that means is you can give me the numbers from a Haney test, but I cannot tell you what those mean in Wisconsin. There hasn't been enough research to say that if you get X on a Haney test, you need to apply Y. I don't have those numbers. I don't have those correlations. I don't have that calibration. So you can give me the numbers all day long, but I can't necessarily tell you what to do with them. I can't give you a number back, a recommendation back. And that's where the standard soil test in Wisconsin, we use Bray 1 for a P and K. We know what, if I get something in a Bray 1, I know what I need to apply. There's that calibration, that correlation has been made. So all sorts of really good stuff. Yes, ma'am. Which one? I don't think I know hyaluronic acid. I've heard humic acid, fulvic acids. Which one? Oh, sure. I honestly don't know. So you stumped me. Good one. All right, A+ for you. I don't know about that product. So, yes, sir. Yes. I don't know. The question online was, can you put too much humate on a soil, and how much? How do you know when you got too much? And I don't know. I'm being very honest. This is what's really cool. So we're living in an age of revelations, right? We're coming through a pandemic, right, that we've never been through before, right? And we're coming into a revolution in agriculture that we've never been through before. So these new products that are out there, I can honestly tell you is I don't know, because the research hasn't been done. And if it has been done, it's been done in a greenhouse. It hasn't been done in field situations. It hasn't been done in Wisconsin. It hasn't been done on our soils and our climates, growing our crops. So I honestly don't know, but there's always too much, right? You can drink too much water, you will die, right? There is a point for everything where there's too much. There's a point where there's too little.
We have a name for that in pumpkin growing, okay? That's called a moron.
A moron?
I know you're new to the giant pumpkin world, but 20 years ago, the world record was under 1,000 pounds. Now it's 2,600 pounds. And a lot of snake oil stuff we're doing in our hobby. But whatever it is, we have over doubled, going on almost tripling in the past 20, 25 years, the weight of these pumpkins. And my question I've always asked, what is it? You know, I don't think it's one thing.
It's not one thing.
Is it, what's the top 5 things that we're doing?
Oh, shoot. So online, they've been asked me to name the top 5 reasons why pumpkin weights have been doubled in the last 10, 20 years. That was what you just asked me, right?
Oh, okay, I'm sorry.
So I think that was your question. Now I'm freaking out. So you can't see behind the mask. I'm like, holy moly, how do I answer that question, right? Is some of it genetics? I would argue it's genetics, a lot of it. I will argue a lot of it is just us getting smarter. I will argue with nutrients, with amendments, with techniques and strategies that may be outside the realm of some of these new products. I would argue that some of it is climate. So it is happening. So I don't know if this room is okay with climate. Me saying the word climate change, but I'm going to say it anyway. Our climate is changing. Our weather, I can say it this way. Our weather patterns are changing, right? So at least in Green Bay, I now have I can plant 2 weeks earlier than I could about 15 years ago, right? My ice-free days in the winter are completely different. My nights above 90 degrees are going up. Our climates have changed. And so does that little bit of an increase in temperature maybe overnight help you or hinder you? More CO2, right? CO2 is a fertilizer, right? Remember that carbon under the air? That's one of the projections is with higher levels of CO2 in the atmosphere, we will see more vigorous plant growth because carbon dioxide is a fertilizer. We need to destroy the atmosphere and get the free sulfur back. I agree. To hell with clean, healthy air, free sulfur. It's all about the giant pumpkins. So I will tell you this, I got to go back to my world. So let me go back to my world. So do you know what the genetic potential of corn grain is, right? I can tell you on average, we yield about 180 to 200 bushel of corn in Wisconsin. Do you know what the actual genetic potential of traditional corn is? It's closer to 700 or 800. That's the genetic potential. I will argue probably the same thing's happening in pumpkins. You have the genetic potential. We just haven't figured out how to manage the system under which it's growing to achieve that genetic potential.
So just for your information, there's a study that's supposed to be done by a professor at Cornell. He's going to figure out what our genetic potential for these seeds is.
Awesome. And I think you'll be surprised. I think the genetic potential of many of our organisms out there are tremendous. We are inhibited by growing season. I'm not from Wisconsin. I am from the amazing state of Iowa, whoop, whoop, right? When you go to weigh your world record pumpkins in Anamosa, that's where I come from, all right? So that's near my hometown, all right? So everything great comes out of Iowa, right? Where was I going with that? Iowa, that was a side note. No, Iowa oftentimes can grow better pumpkins than we can because it's just simply a better climate. You give them the same genetics in a different growing system, it's gonna look different, it's gonna perform different. It's not, or it's not true, right? So here we go, and this is where local climates come into play, right? Yeah, he has no excuse why he's not performing, so just, I don't know what he's doing wrong, but I was born and raised there. I mean, his pumpkin should be like 6,000 to 7,000 pounds, so I don't know what the hell he's doing wrong. So that's perfect. But right, it's the climate. Is the humidity change, right? Humidity plays a huge role in disease prevalence. It plays a huge role in transpiration rates, respiration rates, right? There's small things that we're not thinking about that impact, and this is where my next slide, right? Transpiration plays a huge role in whether or not our plant is taking up nutrients, right? So just because, we'll try and get back on track. Look at this, transitioning back into the slides, right? Transpiration plays a huge role. On humid days, are your plants taking up water? As much water as they are on dry days? No, they're not gaining the weight. They're not taking up the nutrients. So simple things like relative humidity in days and nights will impact how that plant grows. Because not only about the water uptake, but the nutrient uptake that comes with it. Because what this slide is showing you, and if you want to know mass flow, if you want to know how nutrients get to your plants, mass flow is the nutrient moving with the water to the plant as that plant takes up water, right? So as a plant sucks up water, it brings nutrients along with it. You'll notice that most of the nutrients, right, 99% of nitrogen is taken by mass flow. If your plant is not transpiring at high rates, it's not getting nitrogen. If you don't have a root system, and where I was actually going with this slide is if you don't have a root system that's active and growing, prolific within that soil profile, you're not taking up nutrients. So they can be there, but there are many, many factors on changing whether or not that nutrient gets from the soil to the plant itself. Okay. the key here, and when we talk about how plants take up nutrients, is I want you to know, actually look at that last column. It's root interception. We all have this thought that roots grow to nutrients, they bump into them, and they take them up. So when you look at the nutrients that are taken up by root interception, is that a predominant way in which plants take up nutrients? Growing to them, bumping into them, and taking them up? No. It's either water moving to the plant root and taking them up with the water, or diffusion. What does diffusion mean? This side of the room, you've been quiet. Diffusion, moving from areas of high concentration to low concentration, right? Osmosis, kind of the osmosis idea. You'll notice that P and K, phosphorus and potassium, are taken up by diffusion, right? That means that, and they only diffuse, research studies have shown, potassium and phosphorus will only diffuse maybe tenths of a millimeter. They don't move very far. So the plant roots pretty much have to come in contact with them, or pretty darn close, in order for it to take up P and K. So the argument here is when we're talking about soil health, we can, in some of these slides, we're going to talk a lot about compaction, right? We're going to talk a lot about those aggregates, that pore space. That is important because when you look at the uptake of these nutrients, right, we can add fertilizers all day long, but if the root can't actually get to it, the water can't actually flow through the soil to move the nutrient to the plant, it's all for naught. We can fertilize all we want, but the plant won't take it up. This is where soil health comes into play, right? This is where it's not just chemistry, right? I have better sense of how the chemistry works. We've done so much research on it, but the physics and the biology behind moving nutrients from the soil to the plant root are huge. This is why when we talked about aluminum sulfate, why I get so anxious, right, about aluminum, right? Because I know how that root takes up nutrients. And if I don't have the maximum amount of roots out there to exploit the maximum volume of soil I can, because that root has to either move the water to it or it has to come almost in contact with the root. If I don't have those roots, I don't have nutrients. If I don't have roots, I don't have nutrients. This is why I spend so many times waving my arms, talking about don't compact your soils, right? Because I can fix chemistry pretty quick. That's a fertilizer. Once you get rid of your pore space, once you get rid of your aggregates, how fast do they come back? Not very. 5, 10, or more years, depending upon where we're talking about that compaction in the profile. So soil fertility, I will argue every day, is more than just the chemistry. It's the biology, it's the physics of getting water and roots down through that soil. Can you increase transpiration? Reduce humidity.
How about temperature?
How about temperature? So yeah, so realize humidity is, this is where I hated physics. I hated soil physics with a passion. All right, so as temperature increases, what happens? It's physics. All right, everybody under the age of 18, study physics because it's really awesome. All right. So as temperature goes up, the capacity of that air to hold water increases, right? So typically as temperatures go up, humidities oftentimes go down unless there is a large amount of transpiration and evaporation replacing that. So how do you increase transpiration? You're going to increase temperature to a point. So you're going to have to educate me. What's the point? What is the temperature point where pumpkins stop transpiring very much? About 85. I was going to say, I can tell you in corn, it's about 85. So there's a sweet spot. We can't get it too hot because then the plant shuts down, right? But increasing that temperature and decreasing relative humidity will increase transpiration rates.
And where does it start?
And
what temperature does it start at?
That's a great question. When does transpiration start? At what temperature? It's slow. It's lower than 72, right? Your plants are still alive at 60, right? What soil? Okay, you're not normal pumpkin growers. Okay, so sorry. You're untraditional pumpkin growers, right? So what soil temperature do you require? to plant seeds. If you were quote unquote a Jamie Patton going out and planting a seed in the ground just to grow a pumpkin for a jack-o'-lantern, what temperature would that be? 65, okay? So when you're looking at soil temperatures of 65, your air temperatures may drop below that, well below that at night. They're gonna be a little higher than that in the day. The plant is still transpiring. It's just not transpiring very much, right? So transpiration is still going. It hasn't stopped.
Would a plant anticipate the cycles of the day and say, I'm going to have to start transpiring at a certain time of day because it's a daily cycle, or is it every day is totally unique?
Yes and yes. So there are diurnal cycles in plants, right? So there's the active phase during the day where photosynthesis is occurring, right? And then at night, they're called the dark reactions, where we move into respiration, where they're actually breaking down their photosynthesis to respire. So much more respiration at night versus than transpiration. So it's a yes and yes kind of situation. So, yes, sir.
Is there a correlation with growing degree days?
Probably, because a growing degree day, so whatever your base is, a growing degree day is basically the accumulation of heat units over a given base. So the more growing degree days you will have, and oftentimes there's an upper cap to calculating a growing degree day, that 85. So yes, the more growing degree days, which doesn't take into account, this is where it gets all complicated. Yes, that will measure heat units, but it doesn't measure humidity units. So
then what happens in a dry climate, for example, you've got growers, not this year, but that have done well.
you betcha. Yeah, I have no problem growing in a desert. Actually, I'd probably really like to grow in a desert, as long as I had water, right? So this is where in a desert system, right? So I probably won't have the prevalence of all the leaf diseases, these powdery mildews and everything else, these fungal diseases that are the bane of our existence, right? If I know what I'm dealing with, I know I'm dealing with an infertile sand, and I know up front that I'm going to be providing much of the nutrient and water to that plant, and I'm going to spoon feed it exactly when I want to, I should be able to do awesome, right? Because I'm controlling the situation. I'm giving the plant water when it needs it. I'm not waiting for rainfall, and I'm not going to get excessive rainfall. So for those of you, I'm guessing over the last couple of years, you've had just as big a problem as regular producers. Excessive rainfall, excessively wet soils, cold soils. If I was growing in a warm desert climate and I don't have to worry about too much water or too little water because I'm controlling it, perfect. If I'm not worried about all these fungal diseases because my relative humidity is low, fantastic. If I know up front that I need to provide those nutrients and I know what the plant needs, fantastic, I do it. There's no excuse for not being able to grow a good pumpkin. You just have to know what it needs and, more importantly, be able to supply it to it. So of course there's some limitations. There's always limitations, but a desert climate wouldn't be one as long as you can supply the inputs needed. And it's, so now they're all moving to Arizona, right? Or Spain, or wherever. So the role of soil biology, so when we talk about those roots, right? How many of you add mycorrhiza? How many of you know the importance? So this is where this group, I don't have to tell you about the importance of mycorrhiza. You probably just didn't have numbers to put to it, right? So when the research shows that mycorrhiza, so that symbiotic fungus, for us it's going to be endomycorrhizae, the symbiotic fungus that infects those plant roots and goes out and explores the rest of the soil. Mycorrhiza can increase soil exploration by up to 700%, right? That's the citation somewhere down below. But when we look at that, that's incredible, right? When our soils, our nutrient uptake is based upon diffusion, right? Plant roots or that fungus coming in contact with it, increasing the amount of soil exploited by 700% is tremendous. And so research also shown, depending upon the plant and the situation, can contribute up to 80% of the phosphorus, 10% of the K, 25% of the zinc, and you can read that plant requires. So when we look at phosphorus chemistry, phosphorus nutrition in a plant, I cannot overstress the importance of mycorrhizae. Because we know phosphorus, we have trouble keeping it soluble because that changes in pH. We have trouble accessing it because it has to be taken up primarily through diffusion. But I can overcome some of these situations by managing my pH. and making sure that I have the mycorrhiza out there. We'll talk about biologics in a second. I also get really excited about mycorrhiza because you've all heard about the word glomalin. The other substance, again, you don't care about this one. This is what's gluing together my aggregates, right? So when you look at those pretty little aggregates in the soil, they estimate 90% of those aggregates that are creating that pore space are glued together by this fungal exudate. So we can't talk too much about mycorrhiza. How do we facilitate mycorrhiza in our soil? I know many of you add it. In my world, we don't add mycorrhiza. It's not cost effective. Reason for that, we don't get consistent results. Instead, what we try and do is facilitate the growth of the mycorrhiza that are already there. And they're there. All of the organisms that you probably want out there are there. You just have to create the conditions for which they need to grow. The water, the food, and the habitat in which they can grow. How do we facilitate mycorrhizae in our soil? You continue to give them something to eat. This is where I usually spend most of my time preaching. And this is what I do. Preach, 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 preach. Cover crops, cover crops, cover crops, cover crops, cover crops. That is pretty much all I do every single day. Why? My husband is so tired of it. So I make him do it in our garden. We grow cover crops wherever we can. When I have extra cover crop seed, I just throw it in the yard, and we have random stuff growing in our yard, right? Why cover crops? Why? It's a green manure, it's adding organics, but when we talk about these living organisms, everybody believes that in the winter they go dormant. They don't go dormant. They're still out there, they're hanging out, they're just being really slow about it, right? They didn't stop living. They're just kind of waning at the moment. But they still need food. What do you think these guys eat during the winter? They eat each other. That is correct. It is one heck of a scene down there, right? But most of they're cannibals, right? They are. Is some wild and wacky, weird stuff that happens down there. But most of these organisms live with what's called the rhizosphere. They live in a very small area around the plant root. Mycorrhizae in particular love to live in a relationship with a plant, right? If we want to facilitate mycorrhizal infection in our pumpkins, we need to make sure that they have a place to live all year round. That means that they have to have a root all year round. They need some place to go because that root is giving them sugars, right? That plant is giving them sugars. Research has shown, and this is what is amazing to me, research has shown up to 60 to 70% of the sugar that a plant makes, it actually gives away to the soil biology. It gives it away for free, right? Because it knows the benefits that those microbes are bringing back to it. So that mycorrhizae, if you want to bulk your number of mycorrhizae, rather than adding amendments, which you go ahead and do, right? You're not making money, I don't care, right? And it's not an environmental contaminant, right? But I would argue, if you want to promote mycorrhizae in your soil, feed them and give them a home. Feed them by giving them a plant root. Give them some place to live. Yes, sir. Ooh. One thing, so do mycorrhizae, so the brassica families. So you said something right there that no radishes, right? The brassica family, so the turnips, the radishes, the kales, the collards, all of these things that we put in cover crop mixes, they do not facilitate a relationship with mycorrhizae. They're non-mycorrhizal. Oh shit. It doesn't mean they kill them, right? It doesn't mean that they're actively seeking them out and killing them. It's just that they don't live in a relationship with them. Neither do cranberries, all right?
If you plant them in with a grass crop.
Right, if you plant them in with a grass crop, then the grass crop will facilitate those. I have a lot of people who want to overcome compaction by just simply planting radishes. No, okay, you won't do that next year. So plant them in a mix. Right? Give that mycorrhizae something to eat. Give them a home, right? That's the key. There's supposedly certain high mycorrhizal plants. I can't substantiate this, but I hear this out in the world. High mycorrhizal plants, such as, for example, flax tends to be a high mycorrhizal plant. I don't know if the science proves that out, but flax is beautiful. Pollinators love it. Throw it in. It's not hurting anything. So, yes, sir. Oh, you're eating my slides away. Sugar. No, I love it. Can we just add sugar to the ground? Not just, right? So they still need a place to live. And that's the cool thing about mycorrhizae, right? They're symbiotic. They're trying to live with that plant. Just by feeding them, they still have a place to go. We really do need that plant host for them. Does sugar do anything? Well, let's answer the other question. Does sugar do anything? It feeds bacteria. Does it do anything? I'm just asking. So this is from a scientific standpoint. Does it feed them? Yeah, but for how long and to what extent? Here's the question. So I have a lot of farmers doing it, and you'll notice that I'm always like, if you add molasses to your soil, I always make this judgment call. Molasses, it's cheap, and it's not, and it adds a little bit of sulfur, and it's not an environmental contaminant. You'll see Jamie's decisions are based upon, is it an environmental contaminant? No. So go ahead, throw that molasses out there, throw that sugar out there. What does it do? A lot of guys will tell me that they really believe that adding that sugar early in the season basically primes the pump, right? That's what it's doing. Add a little bit of easily decomposable sugar early in the season, get that microbial community up and going, right? Give them a jump start so that they're ready to go when environmental conditions are suitable. Does the science prove that out? No. However, am I worried about it? No, right? So we used to, and when I worked in Missouri, we'd take mixed Mountain Dew with a lot of our sprays. Why? I don't know, because because Mountain Dew, why Mountain Dew? High sugar content. They always thought spraying sugar improved the efficacy of some of their nutrients applications and some of their herbicide applications. Does it hurt anything? No. Do I have scientific proof to say it works? No. Go for it though. What do I consider environmental contaminant? Milk is, I had to write a paper, right? This spring, I was one of the leads that wrote on the land application of milk. Land application of milk, it has a huge potential to be an environmental contaminant, worse than manure. Milk in water is much worse than manure in water. And that's really hard for people to grasp. But milk has lactose, it has all this decomposable sugar. So when I put milk in water, I get algae blooms like this, dissolved oxygen like this, fish kills like this, much faster than I'll ever get manure to react. So yeah, it's depends upon who you're talking about. What's an environmental contaminant to me? I'm always thinking water quality. So that's my other hat. I'm constantly imagining what's happening to water quality, what's happening to soil ecology. Yeah. So this is where I really like the question. You notice I forget that I'm wearing a dress today, so I shouldn't do that, right? So I love the dairy industry, right? I work with the dairy industry. This is what's really interesting when you look at some of these byproducts. So some of these lactobacillus are some of the amendments that are being added to the soil to help with organic matter decomposition. Milk, waste milk, for example, when applied, as long as we treat it like a nutrient source, right? And we account for and it's nutritious, for God's sakes, right? That's why we have people drink it. There's lots of nutrients within a milk. So as long as we're applying it at rates that are conducive to our soil fertility plan, right? And I'm not oversaturating that soil. My big concern with using high sugar products like a milk is that I add too much, right? And I drive the dissolved oxygen levels in my soil down and I turn it anaerobic. So I'm adding a liquid material that has a lot of nutrients. The microbes are going to look at it and say, wee, they're going to eat it up, right? And then I'm going to lack oxygen in my system, which is detrimental to nutrient cycling, the rest of the microbes, my plant growth, so on and so forth. So that's my concern with waste milk. But it's just, if we accommodate the nutrient and water status of it, why not? Because that's one of your amendments, right? I mean, I read Little House on the Prairie when I was a kid. Don't you all just take vines and you insert needles and directly feed them bowls of milk? I think I remember that. Nobody read the Little House on the Prairie? I know. That's why I put it out there. You're all looking at me like this woman is an idiot. I know, ladies and gentlemen, I know. Yes, sir. I'm unplugged. This is why they don't let me do this. All right. questions? Let's see what time it is. Let's go ahead. We'll take a question and then we'll take a quick break because I know y'all need to get up and move around. Yes, sir.
Okay, so plenty of us have mycorrhizal fungi.
Yep.
And, whether we're wasting. Up in the soil anyway, and that's maybe not affect us, but I've seen plenty of different tests of my own on the growers. One of the comments, I wouldn't say it's a 52, but something that I would always re-roll on.
Yep.
And
How do you increase the availability of phosphorus in your soils? Tell me your pH. Too high. Let's start by lowering our pH just a titch. All right, and then we're going to look at soluble products. So when we look at when I say soluble product, what do you use as your phosphorus source typically? Oh, check. All right. So TSP, so 0460. So so yeah, and this is where your pH is probably interfering with the phosphorus solubility, even at a pH of 7. So it's going to be placement. This is the other thing when we think about, and I put my mycorrhizal products up here. When we think about these nutrients that move via diffusion, right? This is what's really exciting about those. Placement has a huge impact on whether or not that is going to be available, right? So if I get my nutrients, so for example, sorry, you're not going. Can I go back to the mass flow slide? Sorry, I did it on this screen. I think it's appearing there. Perfect. Nope, one more. There you go. When you look at nitrogen, for example, 99% of it is taken up by mass flow. What that means is that my placement of that fertilizer is not that important. I can put it right next to the plant, or I can put it 2 inches from the plant, or the research shown maybe up to 4 inches away from the plant. And because of depending on my soil texture, that nutrient is going to move with water to that plant. So those nutrients that get taken up primarily by mass flow, placement is not as important. And they need to be close, but they don't need to be super close. Those, when you look at phosphorus and potassium, placement makes a difference, in particular phosphorus. I need to put it in a place where I know that those roots are going to come in contact with it. And so in the strategy in conventional agriculture, what I do in these systems is I band phosphorus fertilizer. And what do I mean by that? In a high pH soil that has low test phos, and I have a traditional crop that I'm growing, I'm going to go out and oftentimes in a 2x2 placement. So 2 inches over and 2 inches down from where I plant that seed. When I plant, I'm running a band. I'm running a concentrated area of phosphorus 2x2 from that plant. Why? There's 2 reasons I do that. Okay, one is I put it in a place where I know once that plant starts growing, it's going to come in contact with it, right? So if my seed's here, my phosphorus here, I know roots are going to grow down and laterally. They're going to grow through this band. So placement mattered. But the band also makes a difference. The reason for that, in that high pH soil, what happens? In a high pH soil, that phosphorus wants to dissolve and it wants to react with calcium in those high pHs, and it wants to become solid again. So basically we add a solid, it dissolves, it reacts with calcium, and it wants to become solid again. So I always call banding like the Twinkie approach, right? So if I have a concentrated area of phosphorus, only the outside area of that phosphorus band is going to come in contact with the calcium, right? I'm hoping the inside center maintains solubility, right? It's like the Twinkie. I have the cake on the outside, the creamy center. So if I can maintain solubility within that creamy center, as that root comes down through that band, it grows through the insoluble, but more importantly, it grows through that soluble phosphorus. And that's how I maintain availability in a mechanized kind of way. So it's about placement, but it's also about how I put that phosphorus in there. Concentrated, right? Because you can imagine if I have a prill, right? A fertilizer, one fertilizer prill, that's going to dissolve. All that phosphorus is going to react with calcium to become solid again. But if I concentrate it, hopefully not all of it becomes concentrated and back to a solid again. Does that make sense?
What source would you use?
Soluble. So do I care? No, oftentimes we see better in row. I can tell you in row crops, I will get better uptake of phosphorus when I use an ammoniated phosphate, right? The nitrogen component of that fertilizers stimulates metabolism of the plant. And that stimulated metabolism of the plant then helps with the uptake of phosphorus. So in my world, the ammoniated phosphates is oftentimes where I go. Does that make any sense?
It's a lot of us water often, some of us might be better to just get started with one and water that and then kind of get some in the soil, you know.
Like I said, it's about placement. So potentially, yes, soluble placement. So that the unfortunate part of this reaction, I wish I would have brought this. The cool thing about this reaction as a scientist is how fast does calcium react to dissolve phosphorus? Like that. That's the problem. It doesn't take long at all. So I can take a calcium and I can take a dissolved phosphorus. I can pour them here, 2 clear liquids. I could pour them right in front of you and it'd turn to a white chalky powder. It reacts just like this. That's the problem with potential problem if you have a pH issue. Sometimes even that soluble phosphorus is going to react because in the low concentrations you're adding, it's going to react as well. So it's a conundrum, and it's based again all back on that pH issue that we talked about probably earlier on. All right, let's take a quick break. I need a drink of water. How much break do you want to give them, Jim? They need to liven up.
10 minutes?
10 minutes. Yes, sir.
I'm from Tijuana County.
You betcha.
I'm a brand new patch that I dug up this spring or last fall.
Oh, dang. I'm sorry, I was looking at your frost levels. Oh, dang.
Yeah.
Where's your K? Over there. Oh, dang.
That was from virgin soil that probably hasn't been farmed in like 20 years.
Yeah, you can tell. Yeah, what's your organic matter percent?
4.7.
Holy moly. Okay, here is, you can tell.
You got your water?
No, I'll be fine. I'll get it. I've got everything. Here's the problem. So this, don't you? So, no. So, oh, we're back to being recorded. So, all right. So, foliar feeding. In my world, right, what do I typically foliar feed? Is micronutrients. And the reason for that, and it's really going to be important. So the research is out in like I said, remember, I'm commercial agriculture. So when we look at foliar feeding, looking at chelated micronutrients oftentimes can overcome some of these issues that we're dealing with pH. So in my world, chelated iron, chelated manganese, chelated items like that is what we're looking at, because you can't apply a lot of nutrient via foliar means, right? So oftentimes either a small amount of nutrient or a nutrient that's needed in a small amount. So that would be the micros. So I know work with foliar humates. So in small scale work with foliar humates are working, particularly in soybean. So it's one of those things, if it works for your system, and that's how you're going to come back. If you're taking those tissue tests, right, in the mid-season, how are you going to come back and correct some of those nutrient issues? That would be with a foliar application of oftentimes those micros.
Give us a simple definition of chelate.
What is the simple? No, there is no simple definition of chelate. No, I'm kidding. What is a chelator? So the micronutrients, many of these are metals. So they're metals, and they want to react with the organic matter to become insoluble. What a chelator does, and a chelator, it means the claw is the word, is Latin for the claw. So it takes that ion, which is a metal, and it wraps it basically in a robe that keeps it soluble, right? So that it isn't going to be reacting with the organic matter and other to be tied up. So chelates maintain higher solubility oftentimes than some of the others, and it becomes oftentimes really important in those micronutrients which are these metals. So even in my world, I use chelated metals oftentimes as foliar applications, particularly to my high value crops. So that's the thing about a chelate. Just remember, it's helping you maintain solubility and increase uptake of that nutrient. Yes, sir.
Can you chelate or increase calcium or phosphorus to something?
No, it's just kind of, that's where there's some products out there that haven't been proven that supposedly you can coat phosphorus with that will maintain its solubility in high calcium environments. Those on a large scale haven't proven efficient. But like I said, there's some other techniques to get around some of this issue with placement and concentrations and things.
Are amino acids considered potential chelators?
Amino acids, some of them can be a potential, the chelates are oftentimes acids. So the most common one is the fulvic acids that you're out there adding. Those help to maintain solubility of those nutrients. I don't know about to be honest, I don't know about the amino acids as well.
One study that I've heard, but not read, something like glycine can make calcium 1,000 times more available to the plant. Yeah.
You got me on that one, sir.
All right.
So question was, and for those of you out in the virtual world, sorry, I need to start repeating this. So the question was about the impact of amino acids as chelators. And to be honest, I don't know much about that. So as we move through fertilizers, reminding us that more is not better. So for you all, I know I've talked with Jim a lot about some of the splitting and the cracking that you see, particularly in the vines after rainfall events, things along these lines. Fertilization can cause the same thing when we get that excess growth, right? Maintaining fertilizers. So when you look at fertilizers, do you change them throughout the season depending upon vegetative growth, right? Up front, what do you use? Higher amounts of nitrogen. Mid-season, we're going to switch to, and later mid-season will be phosphorus for those of you online. And later in the season, we often go with higher rates of, and why is that? Do you know why you switch to higher rates of potassium? For fruit film. Potassium plays a huge role in enzyme activation as well as water regulation. So that's where potassium comes in later on with that fruit fill. That potassium is helping with that water uptake and that imbibing and that management. Go ahead.
What's the relationship between manganese and potassium that regulates uptake?
There are, so there's, and that's where these synergistic and antagonistic effects of nutrients. And this is where maintaining, not applying excess. So we know zinc and phosphorus have a similar relationship. They can be antagonistic. If one is in excess, we'll get lower uptake of the other. So you have to be very careful in looking at these. And I don't remember all of these synergistic and antagonistic, excuse me, I'll get that word out, relationships. But does anybody, there's awesome online. My go-to book is Soil Fertility and Fertilizers by John Havlin. It is the quote unquote typical textbook for most soil fertility classes, and it goes in depth into some of these. So when we look at these relationships, yes, oftentimes antagonism are between, so these are reducing the uptake of one by over applying another. They oftentimes are related in that they're both anions or they're both cations, they're both positively charged or they're both negatively charged. And it's when we're fighting, basically they're fighting for the same uptake mechanism within the plant. So if you over apply one anion, you'll get less uptake of another, and you'll start to see that imbalance and that reduction in growth because of how the nutrients react within that environment, as well as how the plant uptake mechanisms impact those. If that makes any sense. So yeah, it's hopefully, if anything from the last hour, you've gotten that soil chemistry is really, really complex. That's the key, is it's really, really complex. So other amendments, we've already started on some of these. We talked about sugar. How about compost teas? Do we love them or hate them? This is where I did do some research right online about what we all thought about compost teas, and this is exactly what online says. You love them or you hate them, right? Why do we love them? Makes you feel good. All right. So obviously we have an opinion in the center of a room about compost teas. For those of you who use them and like them, why do we like compost teas? So, yes, sir. It doesn't. I get a little worried about some, when we think, I'll be honest, foliar sprays kind of make me nervous at times, right? So there is, when we talk about solubility of nutrients, oftentimes those are salts, right? That's what the definition of a salt is. It dissolves easily in water. So many of these nutrients that we're applying as a foliar application are acids or they're salts, And so this is where I get a little nervous about foliar applications. In addition, I get worried about foliar applications and the amount of nitrogen, right? Because what happens when we over apply ammonium? Yeah, but if we don't go all the way to death, we're getting burned, right? So that as that ammonium converts over to ammonia, we get burns. I guess I don't need that lid. So, but yeah, this is where foliars, like I said, when they're done properly, have an impact. But if they're not done properly, we can have some detrimental effects, either from that salting effect, that acid effect, or that burning effect of those nutrients. So depending upon what your compost tea, and this is where they're all different, right? Depending upon what your compost is, depending upon its composition, I might be really worried about some of these other factors. So when we talk about absorptions, anytime when it's actively growing, right? So when the metabolism is high. So if we want increased uptake, when should we foliar apply? Oftentimes it's earlier in the morning, right? To allow for that uptake while we're absorbing things throughout the sun, time of the day. For those of us that have dew, yes, it is. So, but I think it's in that realm of it really does depend. So the research out there shows that just like the opinion in this room, you either love it or you hate it. So it's either no effect of compost teas as compared to synthetic based fertilizers, or beneficial effects. This is where I'm never going to give you an answer other than it depends. So if we can just establish that right now, right? Because it really does depend upon soil. It depends upon condition. You have humidity, you have high relative humidity, you have wet leaves, right? Others of us don't. Winds, so on or so forth, right? So Kewaunee County, the wind never stops blowing. So things are drying off super quick and I'm not worried about it. Where if you're stuck in the valley, right? You're stuck in the valley, things don't dry off as well. So it really, really does depend. And so this is one and where if you were a conventional farmer, this is how we approach this. We run a trial, right? You try it on a small scale and see how it compares to your standard management. I don't have a good answer for you, unfortunately.
I've heard people use compost teas because of fusions, like after a heavy rain, the soil got eroded, and then they have to bump up the good biology in the soil to bring it back to healthy life.
Sure. So it all depends. So sure, right? All right. Minimizing soil disturbance. Let's go here. How many of us like to till? All right. This is usually where people hate me, right? So I had a wonderful discussion over break about no-till and how changes in soil health with so this is conventional agriculture converting from no-till with a cover crop system, and how just wondrous changes in the soil. So why do we till? I can tell you that tillage is probably the most detrimental thing that we can do for soil physical properties and soil health. I throw this picture up here that I took from Missouri, right? And oftentimes I ask people, what's wrong with that soil? What looks weird about it? The top is absolutely compacted. And usually most people, even if you're not in agriculture, you look and you say, why is the surface lighter than underneath? You notice in this picture, everywhere where it's been tilled, so this has been moldboard plowed, right? Everywhere it's been tilled, tillage introduced oxygen into the system. And when we introduce oxygen into the system, it stimulates microbes to break down organic matter. And we get a huge flush of carbon dioxide out of the soil. We lose our organic matter. We get a huge flush of nutrients, oftentimes that we can't use at that point in time. And we destroy that soil structure through physical means, as well as these biological and chemical means. So this, and like I was telling someone else, usually my job is not to stand here in front of a podium and talk. Usually I have on a pair of boots and a knife, and I'm standing in the bottom of a soil pit showing you everything about that soil profile. That's my usual job. And this is the one thing that I can almost always show people is even after 30 years after a field has been moldboard plowed, typically I can still find evidence of that compaction. I can find evidence of that tillage, even when you've converted over to another system. The damage that we do to aggregation, the damage that we do to that organic matter persists for a long period of time. So why do we till? Why are we tilling? So here we go. This is where it gets really fun, right? So Jamie wants us to plant a cover crop, and then she doesn't give us any way to terminate it, right? So oftentimes we're terminating that cover crop with tillage. We're incorporating that biomass to get a recycling of that nutrient. Does one offset the other? Cover crop makes it better, but does it improve it? So tillage is oftentimes a necessary evil, particularly if you're not out wanting to use a herbicide, right? So the other option for using a cover crop is to come back in and terminate it chemically. So some of us are not comfortable with that glyphosate application, oftentimes that Roundup application. And so if our other option, so if plan A is to till, plan B would be to terminate with glyphosate or another herbicide. What's plan C? Let her go, right? So depends upon what we're using. So what are you using as a cover crop? Pro millet, okay. Ooh, nice, pretty warm season. All right, pro millet. So if you're not familiar with pro millet, a beautiful warm season grass, good root growth, great forage, feed it to his dairy cows. They'll love it, all right? So oftentimes it's not gonna have the same effect. Oftentimes what we're using in these systems is cereal rye, right? So cereal rye is a good overwintering winter cereal. So an option on C, if it grows fast enough, if we get it in the ground early enough, how many have heard of roller crimping? So you basically wait till that plant is almost to reproduction. When the stem is lignified, you come in and you with a roller crimper, which is basically a round cylinder with some bumps on it, and you basically snap that stem. And at that point in the plant's life cycle, because it's going into reproduction, when you snap the stem, you kill it. And you just leave it in place. So we use a lot of this roller crimping in organic production. We use a lot of it even in conventional production. We grow the cereal rye, we wait till almost reproduction, we roll it over, and now I have my own mulch, right? I grew my own mulch technically, come back in and transplant. So I can tell you commercial pumpkin producers use this a lot. If you were a pick your own pumpkin patch, this is an ideal way. You grow your own mulch, you roll and crimp it, you come in, you transplant your pumpkin plants, and now when you're bringing everybody in the fall, they aren't getting muddy, your pumpkins aren't dirty, so on and so forth, because they're sitting on top of a mulch that you grew. So commercial, I work with some commercial pumpkin producers that do it this way. Smallest, depends. A lot of people make their own, right? Because it's not a complicated piece of equipment. It's basically a drum. And so on the smaller ones, you're filling those drums full of water, and they might have some V. It looks like a lawn, exactly. It looks like a lawn roller, except I want to oftentimes to be more efficient, I want a crimp part on it. So maybe you're welding some angle iron on it to give it that V shape so that you're busting up that stem better. So the ones I use for research are 10 foot. So they come in 10, 15 foot. But again, a lawn roller, as long as it's heavy enough, like I said, I'd rather have a crimping action on it. No, it'll pop back up. That's why I want that V. I want that crimp on it to make sure that it doesn't pop back up.
If you cut it down flat, will it grow back?
If you cut it down flat, it will not, at the same growth stage, it won't grow back. So same idea. The key is that you have to get it at this lignified stage, right? Right, head it out. So boot stage is kind of earliest I'd want to do it as a boot, but after that, so usually full anthesis is where we're ready to go.
Well, the reason I use evils of tilling, and for most of us, is we bury our vines, so we need friable soil to have push over our vines. So if we have this big residue of cover crop, it's still rooted in chunks of organic. It's just not
It doesn't work as well.
So we have to manipulate the soil. I don't like doing it, but I don't know. I know Mike says he brings soil from the edge of his bed.
So this is where, if it is, we do have to do it. How do we offset those challenges? So if we are tilling, right? How do I offset those detriments of tillage? So it's just another tillage kind of method. So, but how do I offset? So laying boards, so reducing that compaction. You had what, a cover crops, right? When we till, right, we're losing organic matter. So how do I offset some of these negative effects of tillage? I make sure and I'm adding organic matter back, right? I'm making sure that I have that active carbon source to keep those microbes happy. So whether that is fresh manures, composts, living biomass such as that cover crop, it could be any of those. So it's going to help to offset some of those negative effects. We also have those negative effects when we talk about disturbances. I also put in all the pesticides, right? Because they do, some of them do have an impact on soil microbial communities. So fungicides, for example, do they impact our soil microbial community? They do. So in a large scale agricultural system, the research has shown that yes, we do bump back those fungus, but they're going to come back. So it's probably maybe a necessary evil in conventional agriculture, but I'm seeing come back that year. Again, you all who are looking at 1/10 of a pound, tenths of pounds making a difference, that fungicide may have some issues, right? Soil, particularly if they're soil applied. If they're foliar applied, right, between photodegradation and inactivation, so on and so forth, maybe not as big of an issue. But there are some instances where these pesticides can cause problems. Oftentimes, depending on the chemical, right, they're often seen as a carbon source. So this is where, as a side turn, depending on whatever pesticide we're using, realize oftentimes they're organic based as well. So when they are applied to the soil, they're seen as a food source and they're quickly degraded. So it's one or the other, but all of them are soil disturbances. So alternatives, anybody use mulch? Troubles with mulches. Yeah, there's lots of potential problems with mulches, right? I love mulches. It helps to maintain soil temperature. I will also tell you, this is what's really fun, is this year go out and if you have an infrared temperature meter, right? So take the temperature of the soil that's bare and take the temperature of the soil underneath the plants that's shaded. Oftentimes they're 20, 30, 40 degrees different, right? So when we talk about maintaining soil microbial communities, I want to keep that soil as cool as possible. That's why I like mulches. It may not work in the system, but that's one reason why I like mulches. I like mulches because it reduces evaporation. So the reason why we get some of this vine split when we have rainfall events is because we're getting uneven watering, right? So we're getting excess water and too little water, excess water, too little water, and we're seeing that differential uptake. Mulches help to maintain that soil moisture at a more constant level, but they come with significant challenges. Insects, right? So that mulch is a habitat for potentially pest insects. It's also a habitat for beneficial insects, but it's potentially a habitat for pest insects. It's a habitat potentially for disease. And as you mentioned, that C to N ratio. So what mulches are we using? Pardon? Straw, leaves, straw. So when we look at these, and you probably all read up on carbon and nitrogen ratios. So the impact of carbon to nitrogen ratio. So these high C to N ratio, what happens is the microbes basically see these residues, they see them as a food source, but they don't have enough nitrogen in order for those microbes to break it down. So instead, because there's not enough nitrogen in the residue itself, instead they take the nitrogen from your soil in order to break down those residues. And you'll see your plants become nitrogen deficient, not because the nitrogen is not there, it's the nitrogen's not there because the microbes are using it to break down your mulch. So it's called an immobilization reaction. So that's another caveat with using mulches, right? So are there other alternatives? Like I said, just to offset some of those issues that we see with tillage. It's going to be a necessary evil in the realm. Realize I'm a soil scientist, so yes, I'm going to call tillage evil, right? Because it's just what I have to do. That's my training. So, yes, sir. Right, so the green grass clippings tend to be, they're not as high in the C to N ratio, and they will break down. They don't have quite the immobilization effect. So they do have, oftentimes if you use grass clippings, if they're not dry, you get molds and all sorts of fun. I don't like about grass clippings is they tend to compact. They get smushy, and you tend to seal that soil off. That's a problem. So we're working on that soil to have a good oxygen exchange So if my mulch is laying flat on the ground and is getting really dense, I'm impeding water movement and airflow into that soil. So that's also an issue. All right, where do you all want to go? You look tired. Come on. What do we want to learn about? Suppressive soils or aggregation? Oh, crusts, the bane of my existence. All right. So those of you who keep saying mine too, I bet are you farming beautiful silt loam soils? Yeah, so usually when you say crusting, I automatically go to my favorite soil texture because everybody has a favorite soil texture and mine happens to be silt loams. So what we see is in soils that have high amounts of silt, silts are small, but yet they're not sticky. So when you look at your soil particles, clays are large, but they're not sticky. Silts are medium sized and they're not sticky. And clays are small and they're sticky. So these silts are in this perfect realm where they're nice and small and they're not sticky. So what happens with silts, when the raindrops hit these soil aggregates, pretty soil aggregates up here, there's little balls. Happens to be a silt loam as well. That raindrop hits that aggregate, right? That aggregate breaks apart. And then what happens is, I call it vertical erosion. So we always think about erosion moving soils off the landscape. What happens is when that aggregate breaks apart, I get vertical erosion. I get those sand, silts, and clays moving down and clogging the pores within my soil. That's why the crust appears, is because the pore space is being filled with the aggregates that were destroyed by raindrops. Or overtilling. Overtilling, yeah, you pulverize it, right? And then when you overtill, you pulverize that soil, you get those individual particles, and as soon as you get water, they go and they settle back in and they fill in that pore space. Now, why this keeps me up at night, right? And I talked to some of you earlier about flooding effects. One of the biggest impacts that I see on poor aggregation in our soils up here in the upper Midwest is when I don't have these pretty aggregates like we see on the screen here, and I have that crust instead, or I don't have that pore space. When I do get rainfall, the rainfall can't move into the ground, right? Instead of moving in, it either sits there if I don't have any slope, and now I have this ponded effect, I have this saturated condition, which is bad for growth, or I get that water moving off. And as soon as that water starts to move off, it takes soil particles with it, and I get tremendous soil erosion. So my thing is aggregates control pore space. I have to do everything I can in my power, particularly at the surface, to maintain those soil aggregates. So how do we prevent crusting? We don't overtill. The other thing I have to do is to get them to build. And so I know I'll come back to the slides. How do we build soil aggregates? Keep going. Sorry, I forget that you can't see what I see. There you go. So this little diagram, I know you don't even want to look at it because it's so complicated and there's so many words on it. But basically, we're going to look at the top lines. How do I get those soil aggregates to come back? It takes a combination of these 4 factors. Fungal and bacterial activity. So basically, it's kind of a sequential process. If I want to get those aggregates back, I want to get that pore space back. What I first need to do is I need to get those roots down in that soil. I need get those roots. If you've ever pulled out a root system and you see all those clumps of soil held to it, right? I need to get those roots down, helping to kind of bring those aggregates, those soil particles together, right? Once I have those root systems helping to bring those soil particles together, now I'm relying upon my bacteria and fungi to further tighten them up into that aggregate. And I'm relying on those bacteria and fungi to start to produce the glues to get them to stick together. Faunal activity, so that means like earthworms, can help me by helping to push those soil particles together. And you'll notice those mineral interactions, that clay, that calcium, those base cation can help to bring that together. So to rebuild those aggregates, I need roots and I need fungus to help to bring those soil particles together so that they can be glued together by those microbial exudates, by that fungus and that bacteria, by the soil organic matter. I need the faunals, those other organisms to help push them together. And I need those clays and those calciums and those magnesiums to help hold them. It's a long process. But you notice, where did it start? I started with Roots. I started with roots. And this is what's really hard for many of us is we in our production systems haven't thought about having roots all the time, right? So when you grow even that little cereal rye crop or you grow that pearl millet, what is that doing? It's providing the roots. It's helping to do this. It's providing the habitat for those organisms that are going to produce the glue. So when I talk about soil health, the words that always come on, the one word that always comes out of my mouth, it's roots. It's all about the roots. That's where this starts. So once I get them, once I get those aggregates, this is where, why do I have soil aggregates? So I went back to this, the soil profile. Why soil aggregates? This is, if you're familiar with, I was in a soil pit up near Crivets, right? This is why we dig holes in the soil. This is why Jamie brings a shovel with her all the time. How does that surface look? Looks really good, doesn't it? High organic matter, lots of good aggregation, and then what happens? I love that you think it's a rock because it sure as heck looks like a rock. That's soil. That's a plow pan. So whether it be rototiller, whether it be double digging, whether it be tillage, I have surface aggregation, but I don't have subsurface aggregation. Okay. So what happens in this soil? It happened to actually have a 1/4 inch of rainfall on that soil, and I was actually out there talking to the producer about why he didn't need tile drain, right? Because he was talking about how his soil is always wet after a rainfall, and he wanted to tile it. I said, there's no need to tile it. The water isn't coming from below, it's coming from above. It's getting stuck in your soil profile behind that soil compaction. So why soil aggregates? Again, water, air movement, root growth, all of that nutrient acquisition. So we have to start by protecting what we have. So why is your soil crusting? It's due to tillage, right? It's due to tillage pulverizing that. It's a physical destruction of those aggregates. It's that chemical and biological destruction of those aggregates that we lose that structure. It also would help, and I don't know if the soil is bare. Typically crusting occurs when the soil is bare, when we don't have a mulch or a piece of vegetation, plant residue, something on there to protect that soil from raindrop impact. So I got to protect what's there first, because this is what I want my soil to look like. Then I have to rebuild it. So compaction, everybody just takes it as a grain of salt, right? We know that in a typical system, depending upon the compacting agent, anywhere between maybe 60 and 90% of compaction happens on the first pass through the soil. And I've done research on this, whether it be whatever you're doing. So take your gator and drive across your lawn. 60 to 90% of all the compaction created by that gator is through the first pass. You could drive 4, 5, 6 more times, and you're not going to see as much compaction occur on that 4th, 5th, and 6th time as you do on the first pass. So any implement, when we talk about climbing, walking boards and all sorts of things, anytime we can do to stop that compaction is important. Because when we look at yield loss, it's anywhere between 20 and 50%. For all these reasons that we talked about, whether it be water movement, whether it be air movement, whether it be nutrient acquisition, whether it be the life of those organisms. It improves root growth. You'll notice the picture on the left, right? See that amazing plow pan? This is one of those, it's a river, a really dark river soil. It was next to the Missouri River Valley when I was down in that area, right? What do you notice? That root that it looks like it's growing down was actually growing sideways at me. So when I took that soil pit, roots had grown down and then grown sideways. So we talked about radishes as a cover crop briefly, right? So that's the picture on the right. What do you see about that radish? That's a really bad sign. Pardon me? It curled, right? We call that J-rooting. So the root came down and then it curled back upon itself because it hit a layer of compaction. So all of these we know are impacting root growth. So this is why moving to an aggregated system. This is why if we can get organics and cover crops, I know cover crops are really hard in your system. They do have some risks, they do have some challenges, But having that root all season long is very, very, very important to maintaining soil biology and maintaining life. So here's another, this may look more like your soils in this area, in some of your area. So those heavy red clays. Again, looking at that soil, there's never a soil pit I go in that I don't see compaction, ever. I go in tens and 10, 20, 30 soil pits a year. There's not a one I don't see compaction in. So how do we create them? We need to, how do we recreate those aggregates? How do we get rid of, you notice in this picture is platy structure. You notice how all the aggregates are laying horizontal. They're large and they want to lay horizontal in that soil. We need that cementation. We need that compression, right? Here's where we've already talked about this. Roots, 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 roots. If I can get roots, if you can rotate out, I don't know how you're set up, and I'm sure everybody's is different. If we can rotate plots, right? Getting some rotation in there is going to be important. I love the idea of the warm season grasses, right? If we could take a year off and we're not growing pumpkins in a spot, things such as sorghum Sudan grass, your pearl millets, mixing in some of these other legumes that we might have, crimson and bursting clover, maybe some vetches, maybe moving into some of the brassicas, even though they don't have that mycorrhizal infection, they have a different architecture of roots. All of those, getting that really, sunflowers, I like sunflowers oftentimes in cover crop mixes, flaxes, things that all have different root architectures that provide that organic matter, that provide that root, or as that compression agent, but also as that habitat for organisms.
What you thought on using mustard as a cover crop?
Ooh, what are the benefits of using mustard as a cover crop? It's a brassica, right? So it doesn't have that mycorrhizal infection, but you saw my eyes light up. Woo! What about mustards? Yeah, are kind of exciting. Huh? They can be used as biofumigants. So depending upon if you have issues with some of the nematodes, for example, we know that they produce biocyanides. So what you do is, and this is used often in vegetable production, you grow some of those brassica species. Pearl millets are actually used in can be used in potato production. You grow the plant simply to use it as a biofumigant. So you grow it and then you till it directly into the soil. And oftentimes, depending upon the system, you may put a cover over the top of it to trap those biocyanide gases that are being produced to basically biologically control nematode issues in your soils. So there's certain ways when we think about cover crops, they do more than just build soil health. They can actually be used in this, mustards in particular, in this way to reduce nematode populations. I would put it in a mix. And this is where, that's the problem. This is where no good deed goes unpunished, right? So.
Better off using a clover or alfalfa, something that would be a little more disease suppressive than a mustard.
In potato production, I'm doing some work up in Antigo on using sorghum Sudan grass rather than a mustard as a biofumigant. So they were using the millets, so these grass crops instead. So when you look at potato production, they don't grow potato every year. We have off years, and so we need to reduce those root knot nematodes that are causing disease. Like I said, we're instead using a grass species, which we know these warm seasons have beautiful root systems on them, really tremendous biomass production. So I could get not only that soil health benefit, but also potentially some biofumigant benefits from it as well. So there's options out there. Let's be honest, we're still learning. So we may learn that there's a new crop tomorrow that can be used in a similar way. But oftentimes, everybody asks me if I'd rather have diversity or roots. And so in many of our systems, particularly up here, up north, I don't have options for diversity. I just need to get a cover crop in. To me, if we had to choose between cover crop or no cover crop, I don't care. Go with the cover crop, even if it's not diverse. I want that root in the system. It's all about the roots. You really are not as lively as you were before. All right, come on, the break really did bad things to you.
So we're soil diseases, root disease. I know a lot of what we talked about relates to that, a lot of us go in the same
Yep.
soil every year. What could we be doing? Probably going back to what bubble stuff is.
All right, so we'll look at some using soil, so it's way ahead, so keep going. So looking at how does soil health impact some of our pest cycles. So there is some potential, some work out there. If we have, and like I said, in the commercial world, we look at improving beneficials. So there's a lot of work right now on using prairie strips to use them as basically beetle habitats, so that we can use those as predators within the system. How does improving soil health, so if I have a better microbial community, a better macrofauna community, how does that impact pest cycles, such as particularly those when we are looking at cucumber beetle right here on the screen, since we know in particular the larval stage of that pest life cycle is in the soil. How does soil health impact these? There is the potential. We don't have great data to document the parasitism of some of these organisms or the death of some of these organisms with healthy versus unhealthy soils, but we do know what happens. Anecdotally, I can tell you in many of my cover crop systems, slugs, particularly on sandy soils, slugs, sandy soils, and cover crops tend to go hand in hand. But I can tell you that over time, as we build soil health, that slug problem disappears. I can't quantify it, but I can tell you it does. And the basic understanding at the moment without documentation is that when we bring back these proper soil food webs, when we bring back predators and preys, when we set up an ecosystem that is healthy and is functioning, that even though early in the beginning we may have some issues with pests, over time that pest problem can potentially be mitigated when the ecosystem comes back into check. So there are some soil health benefits not only for pests, but for weed seeds. Right? So we know that a lot of the weed seeds do not go on. So I work a lot in water hemp, for example. Huge issue in the state of Wisconsin. So each plant produces close to 250,000 seeds per a single plant. So trying to reduce the viability of that seed within the soil health system, either through parasitation by those pathogens and fungi, or predation by other organisms that are in here. But what what Jim wanted me to talk about mostly was the disease cycle. So how does improving soil health improve plant disease? So are there such a thing as suppressive soils? I know you've read about them. I know you're very knowledgeable and you have an opinion about them. So are there such a thing as suppressive soils? I hear the words, so if there's online, they said yes. Well, it depends upon what you're suppressing, right? So are there such a things as suppressive soils? Have you seen it? And what is it? I guess I should define what is suppressive soils. There's soils in which a pathogen can be introduced, but it does not establish or persist, or it establishes but causes no damage, or it causes some damage, but over time the plant community adapts, and so that the pathogen is less likely to persist and cause disease in the soil. I liken this to, oftentimes when I talk about soils, y'all just stare at me like, what does that mean? So when we think about it, so Staphylococcus A, right? Staph infections, right? We're all familiar with that. I have to bring this back to human health, right? So staph A, right? Many of us are carriers, right? Probably, I don't know, 30% to half of us are carrying staph A right now. But we don't have a staph infection, and we probably will never develop a staph infection, yet we still harbor that organism. Why is that? We're suppressing it, right? It's called an immune system. In a human, it's called an immune system, right? We're suppressing that pathogen. It's here, right? We may be introduced to it and it doesn't persist, or we may introduce it, it's maybe introduced to us, it persists, but it doesn't cause us any damage. I may be able to transfer it to you and it causes damage in you, but it doesn't cause damage in me. Or I might have had a bit of an infection, but now I've become resistant to it and I can harbor it. and it doesn't cause me any issue.
So does plant residue create that or not?
Oftentimes, so is it the plant residue that's causing a suppressive soil? The argument is, and please realize there's a lot of argument about suppressive soils. And we skipped the slide where I said I'm not a soil microbiologist. Jamie is a soil pedologist, right? There's a lot of argument whether these soils exist. We know they exist, right? We don't know why they exist exactly, but we do know that they exist because they exist, right? We're technically suppressive ourselves. So for those of us to bring it more back to COVID, some of us had COVID and were deathly sick. Some of us had COVID and died. Some of us didn't even know we had COVID, but we had COVID, right? It all depends upon ecosystem and ecosystem, individual to individual. So the research suggests, does it exist? Yes. It suggests that over time, plants build immunity and soils build immunity to pathogens. Maybe that's Phytophthora, if you're worried about some of these rats. Maybe it's some areas that have powdery mildew populations that never seem to go away, right? In my world, you work with white mold terribly in soybeans. Some fields never have white mold and they can be right next door to one that does. Why? We attribute it probably back to some kind of biological origin in the soil. There are such a things as pathogens that will suppress it. We know this because we can sterilize the soil and it goes away. We know this because when we talk about suppression, particularly specific suppression, we know that if we have an area that is resistant to Phytophthora rot, for example, that we can transfer soil from that area to a new area, and we can bring that immunity, we can bring that suppression with us. So this is oftentimes one of the arguments when you look at the addition of composts over time, depending upon where the source of that compost, that fresh organic matter addition, along with the fresh introduction of some different soil microbes, potentially can bring in suppressive factors within our soil. So it's not only the combination of the organism, but that fresh carbon source that facilitates the production of these, or the reproduction of these organisms and the proliferation within the soil. The argument is, right, that everybody believes that a more diverse system is better. A more diverse soil system is more suppressive. The research is showing that's not true. So for many of us, if anybody ever done a soil health test, where says you have X number of bacteria and your bacteria to fungal ratio is this, they're often called body phospholipid fatty acid test, tries to give you an insight into your soil communities. What we're finding is it oftentimes doesn't matter the diverse number of organisms. It's more important about which organisms are there. It's a specific community that is causing that suppression. So this whole idea of trying, and this is where I get a lot of questions, can I measure the diversity in my soil? Can I use a test like a phospholipid fatty acid to gauge whether or not I'm moving towards suppression? The answer is no, because it's very, very microbe specific. They exist, but we can't tell you exactly why they exist at this point in time. Certain organisms we do know, certain organisms we don't.
Okay, so we talk a lot in our world about the good guys versus the bad guys, and we buy products to inoculate the soil with good guys, and we're going to outnumber the bad guys with the good guys.
Right.
And so we also hear about, I think we have this idea that anaerobic soil is disease soil and aerobic soil is healthy soil. Good guys grow in either type of soil, the bad guys grow. I know
Yep.
3 or 4 questions.
No, they do. And so there's good guys and bad guys that are both anaerobic and anaerobic. There's good guys and bad guys out there. Can we add them? So I've done a lot of discussion with soil ecologists. So again, this is not my area, so I spend a lot of time talking to really smart people. And I can tell you the really smart people that I work with are more excited about improving soil health rather than that is naturally there, rather than adding organisms to that soil. So most of the time, it's basically the field of dreams. So I won't give you his name, but down at UW, so I've heard this from 2 soil microbiologists. If you build it, they will come. right? And I think this slide, when we think about this, depending on your product, can we add beneficial organisms to the soil? Issue with adding beneficial organisms to the soil is that many of these products are not regulated. So you don't know who is in that solution. You don't know how many are in that solution. You don't know if they're safe for humans. So there's a new product out in my world that is a free living nitrogen fixer, right? So it is a Klebsiella product. So Klebsiella is the genus of the organism. Anybody, so dairyman, tell me about Klebsiella. Yes, Klebsiella. Klebsiella. So when I read this product label, and I'm like, holy moly, the Klebsiella species that they were using is a human pathogen. So it causes severe infection in humans. So I can tell Klebsiella to any dairyman and they freak out on me, right? This is the product that's being marketed and is being sold and is asked to being applied by a farmer to his soil, and it's a human pathogen. So this is some of the issues. When I think about some of these products, I get really nervous. Some of them will be aspergillus, for example, right? Anybody heard of aspergillosis, right? When we look at fungal species, how about blastomycosis, blastomycetes? I don't think we know enough about many of these organisms to actually start manipulate them. This is a Jamie opinion. I can tell you that the Klebsiella product, I looked it up, and if you look at the warning on handling warning on it, I don't think any farmer ever read the handling warning, because if they did, they would have put the product back down.
Doesn't necessarily mean it's bad for the plant.
Doesn't mean that it's bad for the plant.
You know, Prudent has oil 157.
Sure. Well, that's not the only thing manure contains. So, right. But I worry about them. Do we know enough about a product? Do we know enough? So the product that I do add, right? When we think about it, and this is where, can a few billion cells that we're adding be competitive against the trillions of cells that are out there, right? So if I want to add a product to a soil, and I already just explained to you that there was 1 billion microorganisms in every teaspoon of soil, and you want to go out and put on a product at a few ounces per acre, and there's 1 billion organisms, how are they ever going to compete? Does it mean that these products are ineffective? No. Everything works once, right? That's why it's a product. I'm arguing that we cannot generalize that these products are going to work for everyone. They may work for some of you. Arguably, those of you on sandier soils, right? Low organic matter sandier soils. I work with a lot of vegetable producers in the central sands where we add biologics, right? They make sense in a system where I can't maintain microbial communities because of the natural soil conditions. So in a high value crop, adding a biologic is giving me a benefit. In a different soil, is that true? No, I can add the same product in a sand, and I go out and I put the same product in my healthier clay soil, and I don't see the same effect. So I'm not poo-pooing these products, because many of them have sound research. Oftentimes it's done in a laboratory, in a greenhouse study, and not a field study. And it always comes back to me talking about soils as individuals, right? Can I guarantee that this product is going to help your soil in your climate, in your management system? No, I can't. But there are many, 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 many of them out there. So the thing is, if you add them, right, will they survive? Do they survive if you till the soil? Do they survive if you decrease their organic matter content, if you mix them into the rest of the soil? When you think about surface applying a few billion cells and then tilling it into the soil and introducing it to the full microbiome, do you think it's going to survive, or will it survive? How about when you put them in environmental conditions? Many of these organisms, particularly these free-living nitrogen fixers, are from tropical areas. So what happens when I bring that tropical organism to Green Bay, Wisconsin? Is that organism going to live? Is it going to survive? So I'm not poo-pooing them, and I'm guessing some of you use them quite regularly and like them and are seeing benefits from them. But I'll tell you, the research and the microbiologists I talk to, we don't have a consistent feel for how these products were out there yet. The mycorrhiza products have been out there for a while. I had the question usually, Jamie, one strain of mycorrhiza or multiple strains of mycorrhiza? If I'm going to use the product, which do I go with? The one that works, I heard. Back of the room, what do you think? Multiple. Why would you go with multiple? More is always better.
More odds.
More odds. So, diversity. So actually what the research is showing oftentimes, if we're leading towards mycorrhizal products, the research is leaning towards multiple organisms. Why? Well, as we get a better understanding of mycorrhiza, we're finding that maybe there's a different organism that infects early season versus mid-season versus late season. They're not all the same organism. There's going to be certain organisms that work better in sandier soils that are drier. There are going to be some that are better off in the wetter soils, the colder soils, so on and so forth, because of the diversity of soil environments, not only on a large scale, but within a small scale. Not only because of the time changes and how the species infect, we're going to see oftentimes one or more strains. So just threw in some research as I was doing there. So looking at native communities, I realize it's Cameroon, but they looked at 4 genres. So the Guamos and the Echospora were the most abundant. So most of them were in 2 genus when they looked at natural systems. Yep.
Is placement important, or is that really to take off?
Placement's going to be important, right? So if me, right, it usually takes a couple weeks, from what I've been told, it takes a couple weeks for that infection to occur. But I want to make sure that my roots are going to come in contact with those spores. So ideally, probably, there's propagules and spores. But I want to make sure that the roots come in contact with those spores. So depending upon how your root system goes, right, that's where I'm going to be putting it. In my conventional systems, right, I oftentimes put it right in with the seed. So I'm seeding alfalfa, it goes in with the seed, and I know that placement is right where it needs to be. If I'm looking at a larger row system, right, mound system for their plantings, in corn, I put it in the row. I don't put it in a row. I put it right where I know that plant is going to come in contact with it.
All these products we're talking about, do they work better under, what do you consider the great conditions for moisture? A lot of moisture, somewhat dry?
It's going to be species dependent, right?
Yeah.
So realize that 90% of all plants on Earth typically have this mycorrhizal infection. So that means desert plants versus wetland plants versus our temperate climate plants. So everybody has this mycorrhizal infection. So it's going to be species based. So depending upon the system, who is doing the infection and who is assisting that plant could vary dramatically from year to year, could vary dramatically from spot to spot within the location. What we have found is, when do these products shine? When we have stress, right? It's not under the quote unquote normal growing season. It's under times of high moisture stress or times of drought. This is where these products really shine. If they're going to show benefit, they're going to show benefit when that system is not ideal. Yes, sir.
So if we're doing a really good job at watering and keeping that soil moisture perfect, is that really going to give us much benefit, or?
It's going to be up to you. So the mycorrhiza, remember, this is an organism, right? So let's recap. Feed it and give it a place to live. So make sure there's plenty of active organic matter, active food source out there, and give it a place to live. So make sure that root system is out there. Give it somewhere to move in. They do colonize from outside, okay? So I do work with our tribal communities as well. And so the indigenous wisdom, so when you go back, indigenous wisdom knew this, right? So if you were to start a garden, right, have you ever heard of elder plants? So when indigenous peoples would start a garden, they would open up an area to produce a garden, and they would leave what are called the elder plants along the outside. Oftentimes those elder plants are sunflowers and nettles, some of the grasses, and they always found that if they left the elder plants along the garden to teach the rest of the garden how to grow, they got better productivity. What they were doing technically was leaving a mycorrhizal inoculant along the outside, right? So this mycorrhiza will move, But you gotta make sure, again, key here for mycorrhiza, root, 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 root.
How far do they travel? You know, along strips?
That I don't know. So quite a ways, when you look at, when I mean quite a ways, in my world, quite a ways is a few inches. So, yeah.
Do you use the fungicide, is it beneficial to use these biologics or?
Could be. So versus foliar versus soil applied fungicides, we know that depending upon the fungicide, there is fungicidal action against some of our beneficial fungal communities. So that may be an instance where an introduction of a mycorrhiza is going to be important. I'm not telling you that they aren't beneficial. I'm just telling you that the benefits may be field to field and season to season. So that's all I'm saying.
Doesn't most mycorrhizas take quite a while to propagate?
Establish.
And
Establish and really take growth. So this is why when we look at mycorrhizal communities, right? So they're more prolific in perennial vegetation. I always like to ask, what's the largest living organism on the face of the earth? And where does he? It's a fungus, right? And where does he or she live? So I'm gonna give it a sex, right? They're asexual, but we're gonna call it a he or she. Let's call her she. Where does she live? She lives out for at least in the United States. I haven't done my research if we found one bigger. This it's a honey mushroom fungus that lives in the forests of Washington State and Oregon. It actually covers, I forget how many square miles in 2 states. It's the largest living organism on the face of the earth. They've done DNA testing all throughout that area, and it's the same one organism in that entire area. So we know if given time in a perennial type system, they can grow to quite an extent. In an annual system like ours, how far do they grow? It's really going to be soil dependent because they don't have that time period to really proliferate. Yes, sir.
In your world, what is a long time? What violence? We're going to go back to violence along with systems in the company.
So the research, at least from vegetable production, my veggie guys put it on every year, and they see an economic benefit from doing that in a sense. So it is year to year. The problem is if you add it, you're going to have to continue to add it, right? Because the reason it wasn't there is because you didn't have the conditions conducive for growth to begin with. So unless you change something about your system, you're going to have to continue to add it because they're not going to proliferate. Right? They're going to die out each system. This is where it's really hard for people to understand why they have to take probiotics every day. Right? Shouldn't you be able to take a probiotic once and be gone? But no, we have to take them every day in order to continue to supplement an organism that doesn't want to live in our intestines. Again.
I've heard with a septic system, we sell, the probiotics to flush out the toilet around that. And I've heard that every time you flush that toilet, you're not going to.
Yep, I was gonna say the Ridex or whatever product that they sell to put in there. No, there's plenty of organic matter decomposing organisms getting into that system through various sources.
And we're not doing that, but.
There's a lot of inoculation coming from many areas.
So,
So is the free seed action have anything to do with this?
Yes. So obviously, so this is where when we look at soil organisms, most soil organisms, and this is where getting soils too hot is really an issue for me. So when we look at most of these organisms, they're going to like to grow within our non-thermophiles or summer ones. 70 to 90 degrees is about their max, the same as the pumpkin, right? They don't really like high soil temperatures. So when we start to get our soil temperatures over that, we're going to start to see a die-off of many of our organisms. And this is one of the reasons, if you've anybody ever been to Brazil? You'll need to travel more. Awesome, fantastic food, fantastic drinks. You'll also learn when you go there that they never leave, in agricultural systems, they never leave their soils uncovered. The reason for that, they always have to grow something. The reason for that is if they leave their soils uncovered, that beautiful tropical sun at the equator basically bakes it to nothing. They kill off all of those, many of those organisms. And so in order to maintain soil health and productivity, they always have to keep it shaded. And they do that by growing plants. So this is the key. Can soils get too hot? Yeah. Do they slow down when it gets too cold? Yes. They don't stop, they slow down. So research up in Menominee County that I've done, actually many of my organisms were more active in the winter than they were in the summer. So many of my ground negatives actually took hold. And so that soil, that nutrients were still cycling, those organisms were still alive, they were still contributing to soil health.
So these microalgae don't freeze off, you're saying?
They do, so they, what the mycorrhiza, from my understanding, what they do is they do go into basically a dormancy type state, they produce spores, and they will regrow in the coming year. So again, not a microbiologist, now I'm speaking outside terms.
Okay, many of us, if not all of us, who use these products, especially microbiology, we're starting it off like threatening the seed with popping the radical. So when we think we're doing this colonization like days after it happened, and so when we grow in soilless mixture, so it's sterile, and so here we know we have this hottest plant that has nothing but good guys. So we put in the soil, we let that plant have a head start for all the bad guys that are, you know, basically grow in the lab, lab/greenhouse, and then we bring it to the field, and we give them those good guys a head start.
So in the terms of mycorrhizae, yes, but the other good guys, so when we look at many of the predator prey organisms, so the trichodermas, for example, anybody use trichodermas? Right? The trichodermas are going to help with some of our rat seedlings. So if those aren't interjected till later, you know, those aren't coming in till later to protect us against some of those diseases. So many of them, yes and no. Like I said, depends upon what you're adding up in the forefront. The trichodermas, like I said, have some efficacy in certain situations. So we know their predator preys are out there. And that's where these products, and that's where when I provide the slideshow, I just go through and I went through and looked at all of the research and who is out there. And I didn't give product names, but who is out there that has studies. Like I said, many of them are in greenhouse type situations of who's out here. So some of these bacterial products for disease and insect control, right? The green ones are for the insect control of the Bacillus mycobacterium. Many of these guys, and this is what we're still learning, is not only may they have some impact on disease resistance, but there's also this impact, they're called plant growth promoting rhizobacteria, and they're going to be in these genuses. So they actually change expression of plant hormones. They improve root growth early on in the season. So they're actually changing how that plant is reacting to its environment and is facilitating early season growth, particularly root growth. So those are some new products that are being studied. So if you see those guys in the Bacillus pseudomonas and the Burkholdia species, those are oftentimes grouped into what are called, again, if you want to Google it, the plant growth promoting rhizobacteria. Basically, bacteria that live in the root zone that help promote.
So how long do they live on the root after the time is gone?
Not very long. So remember, why the rhizosphere? So the rhizosphere is that zone right next to the root system. We're talking a few millimeters. Sorry, I'm unplugged. This is where Jamie can't wander and she forgets. All right. So the rhizosphere, right, is right next to the plant root. It's a few millimeters from the plant root. And so this is where these bacteria live. And the reason for that is the plant is actually, as we talked about earlier, is exuding sugars, is exuding photosynthates into this zone to feed them. So there's this beneficial symbiotic relationship going on. There's also this own setup predator-prey type situation that's going on. So once you start to cut off that supply, and this is where you'll see not only roots, but most of the time I'm preaching about live roots. It's about that photosynthate getting back into the system, feeding these rhizobacteria and maintaining them. So this is why oftentimes when I'm talking cover crop species, I'm talking about overwintering species to make sure that I have that live root. What is the impact? Can I quantify it? We're still working on that, but we know there is a beneficial effect of having a live root on these populations, potential suppression. So again, looking at, and this is where I pulled many of these out, and I'll share this with you, looking at bacillus and what are they doing? They're increasing the length and biomass of that root. They're enhancing fruits and grain yields. So there's research out there on that they do work. Like I said, the individuality of soils will work, are different. The fungal products, trichodermas, from what I gather, trichodermas seem to be popular in the giant pumpkin world. Yes, no, yes, no?
There's products out there that may have been more popular a few years ago than now.
So they're moving away from these endophytes. So this is where the endophyte world, so these organisms, they either live in the rhizosphere, on the root, or even can sometimes live within the root. They're getting studied right now. In our world, if you want to look at, this is A4114, the value of trichoderma. And like I said, you're going to find that they don't find any consistent result. Sure.
In the weather, it's from that slightly.
Sure.
Why do cover crop blend by if that turnip and radish question mark? I tried this but found those two do not overwinter. Do they still provide value if they are only growing several weeks in the fall?
Excellent question. So going back and answering that cover crop question, why I would have went with a vetch turnip radish verm. So realize overwintering of cover crops is really species and location dependent. So in my world, right, I can get vetch to overwinter. Annual ryegrass will overwinter. So it all depends upon snow cover. So for those in, for example, Iowa, you're going to have a much different species mix down in that area versus me up in Green Bay as to what will overwinter because of snow cover, because of growing season length. So most of the time when we look at species mixes, I want something for a cover crop. I want something overwintering. Oftentimes we're putting in oftentimes I will go with, it sounds strange, but I will go with a spring variety of a cereal and I will plant it in the fall. So I do a lot of spring barley in some of my cover crop mixes. And the reason for that is that barley, the spring variety, when you plant it later in the season, it recognizes that these days are getting shorter. And so it's trying to go into reproduction as quickly as possible. So you're going to get tremendous vegetative growth because the plant's trying to carry out its life cycle in a very short period of time because it's sensing that shortening of day length. So oftentimes I will put winter cereals mixed in with spring cereals, mixed in with some legumes, mixed in with some other plants. Some of them will winter kill, some of them won't. But what I'm trying to do is maximize biomass production there in the fall, but also maintain the living root. And everybody has a different philosophy on how they mix cover crop mixes. And it will also vary as to what the crop is coming in afterwards. So lots of, yep. So what are our options? What are our options for Wisconsin in October? So if you are south of 10, right? So we can still come in with several different, you can even come in with a spring cereal in mid-October just and get some biomass growth. But most of us are going to be safe with a winter rye or cereal rye that is going to overwinter at that point in time. So we're planting cereal rye even into November in some parts of southern Wisconsin. So in northern Wisconsin, oftentimes we don't go there. I would like it in by October 15th, but it really depends upon location. If you're north of 10, that's my October 15. Winter rye is basically all. You could try a winter wheat, but most of the time it's not as cold tolerant. So those of us north of 10 have some real challenges. Consistently, it's the winter rye. All right, you're slowing down. We need a panel discussion or something. Yes, sir.
Yeah, I'll this.
Yep.
$1,000,000 question is, what soil type and where is it located in the state that would be the highest productive value? Like, where would I move to? So
Ooh. Okay. I like it. All right, Mike, where do you live?
I live in Fond du Lac County, near Greenway County, and Silvermont.
That would have been my first choice. So when not necessarily Fond du Lac County, but I first choice, if I had to pick a soil, I would pick a well-drained, well-organic mattered silt loam. Okay, that's why I pick. Why a silt loam? So silt loams have, if we had this graph, oftentimes silt loams are one of the most forgiving soils that we have. So you can use and abuse them oftentimes and you'll still get them to produce. But when we look at silt loams, particularly for moisture control, this is the key. When you look at it, and I see this graph in my head, so it's hard to demonstrate. But if you could imagine plant available water, right? So the amount of plant available water in the sand between this plant available water is water held between field capacity and permanent wilting point. So now I'm using some big terms, but basically it's the maximum amount of water a soil can hold that will be given up to a plant. In a sand, it's about like this. In a clay, it's about like this. In a silt loam, it's about like this. So it's a weird graph where you have a little bit of plant available water in the sand, a lot in the silt loam, and it starts to taper back down when you get into the clays. The reason for that is we all know sands don't hold water. We understand that concept. But the problem with clays, so when we get heavy clay soil, is the forces of adhesion and cohesion, so that attraction of that water to those small soil particles is really, really tight. Those clays hold onto that water really, really tightly, and the plants don't have enough energy to take it up. So silt loams, because they're that medium size, they hold a lot of water, but more importantly, they give up a lot of water to those plants. So that's why I would pick a silt loam. I'd probably go further south, however, so I would go down into maybe the Prairie du Chien-ish area, right? Sorry. So am I narking you out here? Okay. You're from Prairie du Chien-ish area? Okay, so that's where I'd go. I'd go in Wisconsin. I'd go somewhere where I had I'd be on the top of a hill, right? Where I had my beautiful deep silt loam. But why did I go south? I picked something that had more growing degree days, right? I went warmer.
Okay, so if you had
You're closer to the equator in Prairie du Chien, right? Exactly. That's where I went.
the subsoil, and topsoil, all of a sudden if you could take one and the other one.
Oh, subsoil.
Mix it together. If I can transport topsoil to my place, I want to.
Subsoil versus topsoil. And you and I just had this discussion about layered systems and how much I hate layered systems, right? So we were talking about, so he has heavy clay soils. We were chatting about bringing in better soil and putting it on top. And how do we do that? Well, when we look at water movement in soils, this is what's really fun about soils. So the hell with the PowerPoint, right? They're never any fun, right? When we think about soils, right? Grandma always told us, right? To improve drainage in a flower pot, what do? Exactly. Everybody's grandma had the same idea and nobody's grandma was trained in soil physics. All right. So this is the problem, right? Grandma always told us, right, to put rocks in the bottom of our flower pot to help the soil drain. Grandma was wrong. And she is, it's the only thing grandma was wrong about. All right. But grandma was wrong about soil physics and how water moves in a system. The reason for that and why I don't like layered systems and why sometimes these subsoils cause us problems is that when we have a finer textured soil over a coarser textured soil, right? The pores in the finer, so clayier soil, so pores in the finer textured soils are really small, right? And that forces of adhesion and cohesion, the water gets held in those smaller pores really tight. So when I put a smaller pores over the top of larger pores, you can imagine those larger pores down below, they don't have enough adhesion and cohesion power to pull the water out of the smaller pores above, right? Because the smaller pores are holding onto the water tightly. The larger pores down below don't have enough energy to pull that water out. So water will only move out of a finer textured soil into a coarser textured soil when there are dramatic differences in texture until the finer soil becomes saturated, right? When there's less energy up there. It's looking at, so look at this construction of athletic fields. So anybody know how, and you're looking at me strangely. Have you ever seen a putting green being built? Everybody does, right? This is what we do on our weekends is we go out and watch putting greens being built. So what do we do? So in the bottom, what do they dig down, they put in what? Rocks and then sand, and then they do what? Well, then they're gonna have to sometime put on finer textured soil so we can grow our grass again, right? But we have a layered system. We have fine textured over coarse textured. And there's actually science behind that. It's because you want that putting green to stay green. You don't want to have to water it as often. So that finer pore over that coarser pore will maintain more water than if it was finer pore over finer pore, because of the way in which water adhesion, cohesion actions. I could show you a video. It's from the 1950s. It's fantastic. It's boring, but trust me on this one. It's like an inverted funnel, right? So there's two. So that's if I have a finer textured soil over a coarser textured soil. What if I have a coarser textured soil over a finer textured soil? It doesn't go right out, right? Because it moves right through the coarse textured soil, and then what happens? It sits on top of that clayey soil, that finer textured soil, and you don't get water movement. So whenever you start to get layered systems where we have dramatic differences in texture, either coarse over fine or fine over coarse, water doesn't like to move, right? Because of the forces of adhesion, cohesion, the differences in potentials of water. So ideally, right, this is why I went down to Prairie du Chien again, right? Because what do I have? He has this beautiful loess, right? Wind-blown silt-sized sediment that came from the last glaciation. That's what loess is, right? He has this beautiful silt loam, but it goes silt loam all the way through. You don't have a layered system because you haven't been glaciated. You don't have that nasty, he doesn't have that nasty glacial till, heavy clay soil underneath. He has beautiful, you're gonna hate him. He has beautiful silt loam all the way throughout. He has this right on top of the hill. He's got great drainage. He's got beautiful silt loams. So, he's in the bottom of the hill, but it all washed off. So even better, he got all the topsoil from the top of the hill to the bottom of the hill. But either way, are we seeing? So I apologize. I didn't know, but I'm saying, I honest to God didn't know, but I still picked out the place, right, that has the top pumpkin, didn't I? Or did I did okay, didn't I? So the soil scientist isn't as dumb as she looks or acts. She might be able to grow a giant pumpkin sometime. She could at least pick the right place in the state to grow one, right? They should be. So there should be like a handicap system for giant pumpkin growing based upon, I think that's a great idea. Starting next year. But again, talking about it, if I had a pure sand system, I could make that work too, right? I just remember sands will be just fine. I just know that I have to add water. I have to add nutrients to make it work.
I got a question.
Yeah.
If you're sandy above a water table, does evaporate up to the ground?
So capillary rise. So yes, it will. So it depends upon, and there's lots of different kinds of sands. So not all sands are created equal. So those of you who farm in the central sands, oftentimes you have these coarser sands. They're large sand grains, right? You get really droughty soils. I tend to live in these finer textured sands, so they're really small sand grains. So what you're saying, if a sand is above a water table, does water move up out of that water table into the soil? It really depends upon the size and sorting of that sand. If I have lots of big sands, and they're all pretty much big sands, right? That's a lot of large pores. I'm not going to get water to move up out of that water table into those big pores of the sands. I get very little capillary rise. I get very little evaporation. However, if I have sands that are really small, or I have big sands and small sands mixed together so that I get small enough pore spaces, I will get water to move up out of that water table into those sands. So it really depends upon sands. If anything, which the last discussion we talked about, pores matter, right? Pore size matters, right? And this is why soil health is important. I need large pores to drain water. I need those big spaces to get that excess water out of the soil, but I need small pores to get water to move around in the soil. I need small pores to store water for those plants.
So if we were to add something to our soil, we have any clay soil, any sand, that thing.
Excellent question. What happens when you add sands to a clay? So how do you make concrete? Explain that one to me. How do you make concrete?
Add a powder to sand and rock.
Add a powder to sand and rock. So what happens when I add sand to a clay? You make something, you just make a gigantic mess that looks a lot worse than when you started. You couldn't add enough, my friend.
There's guys that'll bring like 16,000 pounds of sand to the plant, makes it funky growers.
You guys are nuts.
I'm just saying, we're not going to huge fields.
Exactly. So you could, but you're just starting over. So that's where, in that small of area, if you can make your soil be anything you want it to be, go for it. Mine all of his soil, bring those beautiful siltworms in.
How far a subsoil would I have to get down?
How deep do your pumpkin roots go? So I'm guessing it's like most plants, a majority of the plant roots are in the top 2 feet. You're gonna get some that are gonna move down from there, but. So now he's calculating buying soil. All right, questions? This side of the room's kind of quiet. All right.
If I'm going to minimize tilling, should I be adding worms to my mulch cover soil? What kinds and how many? What time of the season should they be added?
So there was a lot of work in basically seeding, inoculating soils with earthworms. So it depends, and this is where and why I'm hesitating is, and this is where my mind always gets stuck, because one, so are earthworms native to Wisconsin? No. So this is where you're hearing me hesitate, because earthworms are not native to Wisconsin. So in forest-derived systems, they're the bane of my existence, and the DNR wish they would go away because they're destroying all of my forest regens. So this is why I always hesitate when we talk about earthworms. So yes, you can get earthworms. There's many different kinds of earthworms. Basically, when we think about 2 different kinds, there's anisic worms, ones that go up and down. Those are the night crawlers. So when you think about those long continuous pore channels that are helping to build building that drainage, those are Lumbricus teratitus. Those are our anisic worms, or night crawlers. There's also redworms. Redworms go back and forth. So it depends upon what we're trying to achieve. Are we trying to improve long continuous drainage? So that's where a night crawler type species would be good. Or are we trying to break up compaction in the surface? These are more of a redworm type. These are called endogenics type worms. So oftentimes you'll get them, but will they survive? That's the key. So
What about season?
what about season?
Yeah.
After it gets warm. So they'll reproduce. Spring would be good.
One last question.
What does chlorine do to the microbes? Chlorine is highly detrimental. It's an essential nutrient, right? But too much, what happens to chloride? So chloride versus chlorine. Chloride is the ion, chlorine is the gas. There are some potential issues with too much chlorides. And this is why you will see lots of people, oftentimes the chlorides are coming from salts. So potassium chloride, sodium chloride, all of our road salts. So there are toxicity effects of chloride on our microorganisms at certain levels. Too much tap water. So is it going through water? So here's where all sorts of fun things. So is it going through a water softener? No water softener water, right? We don't want that. Sodium chloride in that bad boy. We don't want that sodium in our system. It will flush out, right? It'll flush out. So I'm guessing we use softener salt, softened water around here, but chloride. So oftentimes, how do we get rid of them? If you had a fish tank, what do we do if we're going to use tap water in a fish tank? You let it sit overnight. So if you're working for chlorine, the gas, then chlorine gas, then you can just fill it up, let it sit, let that gas dissipate over time, and then that won't be an issue for it. So is iron an issue? No, we have so much, adding additional iron into our system. We have so much iron in our soil, that's why it's red. I'm not too worried about it. High iron in leaves, don't honestly know. So.
Is there truth that plants can take iron in the oxidized form and it isn't really that beneficial to the plant? It's an oxidized form, not a reduced form.
Most of the iron is going to be taken up as iron 2, the reduced iron. So will it take it up as probably oxidized iron? More than likely, but the reduced form is definitely the form that has been most well documented to provide soil benefits. So it's the Fe2, it's the iron, ferrous iron.
I've had
ferric
some-
iron.
Okay, so we'll go back to that. I had a sprinkler on a new house construction, okay, and it's right up against my mortar on the house. It's permanently speaking mortar. It's only doing, well, that's what I'm asking. How much iron you want to handle on the
I don't, yeah, I don't honestly know. That iron would not be chelated, so it's probably just gonna sit. Some of it may be taken up, but more than likely it's just sitting there. It'll be washed off later on. I don't, that's a very unique question to enter on, because I have no idea. I'll be very honest there, not a clue. So, all right, we will shut down Zoom. Thank you all.